Look up at the night sky. What do you see? A scattering of stars, perhaps the moon, a sense of quiet vastness. But what if I told you that this peaceful scene is hiding secrets so strange, so breathtakingly bizarre, that they make the wildest science fiction seem tame? Out there, in the deep and silent dark, the universe is performing magic tricks on a scale we are only just beginning to understand. Black holes that warp the fabric of space and time, ghostly particles that pass through our bodies by the billions every second, entire galaxies made of invisible matter. These aren't fantasies. They are real cosmic discoveries, and each one challenges everything we thought we knew about reality itself. It's as if the cosmos is a master illusionist, and we've only just been invited backstage. Today, we're setting off on a journey to explore 30 of these breathtaking revelations, 30 cosmic discoveries that completely defy logic. From the eerie Great Attractor pulling countless galaxies toward an unseen destiny, to the haunting Great Void where almost nothing exists for hundreds of millions of light years, we will venture into the heart of the universe's greatest mysteries. Each discovery is a puzzle piece that doesn't quite fit, a rule breaker that forces scientists to rethink the laws of physics. This isn't just about facts and figures, it's about wonder. It's about that childlike feeling of staring up at the stars and realizing just how much magic is left to uncover. So get comfortable and open your mind to the extraordinary. Whether you're a seasoned space enthusiast or someone who's simply curious about the grand mysteries above us, this voyage will leave you with a deeper sense of awe and maybe a few questions that keep you looking up long after this video ends. We're about to explore the impossible made real, the mysteries that remind us the universe is far stranger and far more wonderful than we ever dreamed. Our journey begins not at the edge of the universe, but much closer to home within our own cosmic neighborhood. Imagine for a moment that you are a galaxy, one among billions in the vast ocean of space. You are moving, of course, because everything in the universe is in motion. But as you drift, you begin to notice something peculiar. You, along with every galaxy around you, are not moving randomly. You are all being pulled irresistibly in the same specific direction toward a point in space you cannot see. This isn't science fiction. This is the reality for our Milky Way and every galaxy in our local supercluster. We are all caught in a cosmic current flowing toward a mysterious and powerful source of gravity known as the Great Attractor. The sheer scale of this phenomenon is difficult to grasp. This gravitational anomaly possesses the pull of tens of thousands of Milky Ways, enough to command the motion of galaxies across hundreds of millions of light years. For decades, its true nature remained one of astronomy's most frustrating puzzles because it lies in a region of the sky called the zone of avoidance. From our vantage point on Earth, looking toward the center of our own galaxy, our view is completely blocked by thick clouds of gas and dust, obscuring almost 20% of the night sky. It was like trying to find the source of a mighty river's current while standing behind a massive, impenetrable waterfall, but technology has a way of lifting the veil. While visible light cannot penetrate this cosmic dust, infrared and radio waves can. Powerful space telescopes have peered through the obscuration, and what they revealed was even more astounding than anyone had guessed. The Great Attractor is not a single, monstrous object. It appears to be the heart of a colossal supercluster of galaxies, a dense knot of matter known as the Laniakea supercluster, of which we are but a tiny outlying part. This discovery fundamentally defies our earlier models of a more or less uniform universe, revealing instead a cosmic web of breathtaking complexity, with vast filaments of dark matter guiding galaxies into dense nodes and clusters. Yet the mystery only deepens from there. The motion of our local galaxies suggests the pull is even stronger than what this supercluster alone should account for. This implies that something even larger, something beyond the Great Attractor itself, is tugging on us. a potential continent of galaxies so immense it makes our entire supercluster feel small. So while we have named the source of the river's current, we are still discovering that the river itself flows into a far greater and more mysterious ocean. Yet just when we thought we had mapped the greatest structures pulling at our galaxy, an even deeper mystery emerged, one that points to forces operating from beyond the very edge of our known universe. Astronomers, while studying the faint afterglow of the Big Bang, noticed something that should be utterly impossible. They found that hundreds of distant galaxy clusters, scattered across billions of light years, are all streaming in the same specific direction at astonishing speeds of nearly 2 million miles per hour. This phenomenon is not a gentle drift, it is a coordinated rush, a relentless cosmic march that has been dubbed the dark flow. This discovery strikes at the very heart of modern cosmology, challenging a fundamental pillar known as the cosmological principle. This principle states that on a large enough scale, the universe should look roughly the same in every direction and be fairly uniform. There should be no special direction, no grand center, and certainly no preferred axis toward which everything is moving. The dark flow defies this completely. It suggests that the distribution of matter and energy is not uniform on the largest imaginable scales, and that something immense and unknown, something entirely outside our observable universe, is exerting a gravitational pull on everything within our sight. Think of it like this. Imagine you are floating in the middle of a vast, calm ocean. You expect the water around you to move with local currents, but you would not expect every single wave and ripple for miles to be flowing in one unified direction. That would imply a tremendous, unseen force, like a colossal waterfall beyond the horizon, pulling the entire ocean toward it. The dark flow is that waterfall for our cosmos. The sheer scale of whatever is causing this tug is incomprehensible. It would have to be a structure or a concentration of mass so gargantuan that it makes our entire observable universe seem like a mere neighborhood in a far grander metropolis. The implications are staggering. It hints that our universe might be just one bubble in a vast multiverse, and that the gravitational influence from these other, neighboring universes is reaching into our own. Alternatively, it could point to irregularities in the very fabric of space-time that were imprinted at the moment of creation, during the inflationary period right after the Big Bang. Whatever the cause, the dark flow forces us to confront the humbling possibility that the forces shaping our existence originate from a realm we cannot see, measure, or even truly comprehend. It is a ghostly hand from the great unknown, gently but firmly guiding the motion of galaxies, and in doing so, guiding our entire understanding of reality toward a new and uncharted frontier. After confronting the ghostly pull of the dark flow, we turn our attention to a mystery of a very different kind, not a mysterious force, but a profound and unsettling absence. If the universe is a bustling metropolis of stars and galaxies, then the region we're about to enter is its equivalent of a desert so vast and empty that crossing it would feel like an eternity of nothingness. This is the Boötes Void, and its existence challenges our understanding of how the universe structured itself after the Big Bang. Discovered in the early 1980s by astronomers Robert Kirshner and his colleagues, the Boötes Void is a spherical region of space roughly 330 million light-years across. To grasp that scale, consider that our entire Milky Way galaxy is just 100,000 light-years wide. You could fit thousands of galaxies like our own across this void, and yet that's precisely what makes it so bizarre. Instead of the thousands of galaxies astronomers would expect to find in a volume of space that large, they have found only a few dozen. It is a cosmic desert of staggering proportions, a near emptiness that defies all standard models of the universe's large-scale structure. The prevailing theory of cosmology suggests that after the Big Bang, the rapid inflation of the universe and the subtle fluctuations in the density of matter should have created a web-like structure, a cosmic web with dense clusters of galaxies connected by filaments and separated by vast, but not entirely empty, voids. The Boötes Void, however, is not just any void. It is orders of magnitude emptier than predicted. It's as if you were walking through a forest and suddenly stumbled upon a clearing so enormous you couldn't see the trees on the other side, a clearing that by all rights shouldn't exist. So how did it form? One compelling theory points back to the earliest moments of the universe. During the period of cosmic inflation, quantum fluctuations were stretched to enormous sizes, seeding the regions that would eventually become both the great clusters and the great voids. It's possible that several smaller voids merged over billions of years, creating one supervoid through a kind of cosmic consolidation. Another, more speculative idea suggests that the void could be the imprint of a collision with a parallel universe in the multiverse, a bubble that brushed against our own and left a scar of nothingness in its wake. And then, of course, there are the more unconventional explanations. Could the void be the result of a Type 3 Kardashev civilization that has somehow harnessed the energy of entire galaxies, leaving behind a region of space that appears dark and empty to our telescopes? While this idea captures the imagination, most scientists consider it highly unlikely, as even the most advanced civilization would struggle to explain the sheer gravitational mechanics of such a vast emptiness. The true significance of the Boötes Void lies in the profound questions it forces us to ask. Is our universe truly uniform, or is it lumpy and uneven in ways we are only beginning to comprehend? This great nothingness is not merely an empty space. It is an active subject of study, a laboratory for testing the limits of our theories about dark matter, dark energy, and the very fate of the cosmos. It reminds us that sometimes the most powerful mysteries are not about what is there, but about what is missing. Now, if the vast, haunting emptiness of the Boötes Void leaves us feeling a certain cosmic loneliness, our next discovery offers the electrifying and equally unresolved possibility that we are not alone. It is a story that begins not with a void, but with a sound, a single piercing note that rang out from the cosmos and then vanished without a trace, leaving behind one of the greatest what-if scenarios in the history of science. This is the story of the WOW signal. On the evening of August 15, 1977, the Big Ear radio telescope at Ohio State University was engaged in its routine but monumental task, systematically scanning the heavens for any sign of artificial radio transmissions that could indicate intelligent life beyond Earth. This was part of the ongoing search for extraterrestrial intelligence, or SETI. The telescope worked by listening to a narrow slice of the radio spectrum around the frequency of 1420 MHz, a quiet band known as the water hole, where cosmic background noise is minimal and which many scientists theorized would be a logical channel for interstellar communication. For weeks there was nothing but the expected cosmic static, and then, for exactly 72 seconds, everything changed. The signal was so powerful and so perfectly matched the profile of an artificial transmission that it overwhelmed the telescope's receiver. As the data printed out on continuous feed computer paper, a young volunteer named Jerry Amon reviewed it the next day. He was stunned by what he saw. The alphanumeric sequence representing the signal's intensity read 6 equals UQQ, but it was the raw power represented by the number 6 that was extraordinary. Circling it, Jerry Amon simply wrote one word in the margin: WOW. The name and the legend were born. What made this signal so special? First, it was a narrowband signal, meaning it was concentrated on one specific frequency, much like a radio station here on Earth. Natural cosmic objects like pulsars or quasars broadcast across a wide range of frequencies. This was a clean, pure tone. Second, it exhibited a telltale frequency drift, precisely matching the kind of shift you would expect from a signal originating from a planet or satellite moving relative to our own. It came from the direction of the constellation Sagittarius, in a region seemingly empty of any known stars or planets at the time. The most frustrating part of the mystery is that it was never heard again. Despite numerous attempts over the decades to redetect the signal from that same patch of sky, using far more sensitive equipment, the silence has been absolute. This one-off nature is what fuels both the intrigue and the skepticism. So what could have caused it? The most tantalizing possibility is, of course, that it was a genuine transmission from an extraterrestrial intelligence, a cosmic hello that we happened to catch for just over a minute. If so, the civilization responsible would need to possess a transmitter vastly more powerful than anything we have on Earth, likely focused directly at us. Skeptics have proposed other explanations. Could it have been a secret military satellite transmission, or a reflection of an Earth-based signal off a piece of space debris? The specific frequency of the WOW signal is protected by international agreement, reserved exclusively for radio astronomy, making a terrestrial source or a passing satellite highly unlikely, though not entirely impossible. Some have even suggested a natural cause, like a comet emitting hydrogen, but the comets in that region were not in the right position at the time. The legacy of the WOW signal endures not because it provided an answer, but precisely because it did not. It remains the most compelling, unexplained candidate in the history of SETI, a singular event that perfectly matched what scientists were looking for. It is a ghost in the machine of cosmic discovery, a brief, brilliant flash that continues to defy logical explanation and serves as a permanent reminder that the universe might be waiting just once to say its piece. If the WOW signal was a brief, tantalizing whisper from the cosmos, our next discovery presents a mystery that has been shouting at us for years, refusing to be ignored. It centers on a single, unassuming star, 1,400 light-years away in the constellation Cygnus. To the Kepler Space Telescope, it was simply known as KIC 8462852. But to the world, it has become famous as Tabby's star, named after the astronomer who led its investigation, Tabitha Boyajian, and its bizarre behavior has ignited a firestorm of speculation, challenging our very understanding of what can happen around a star. The Kepler telescope's primary mission was to find planets by staring at stars and waiting for them to dim. When a planet passes in front of its star, it creates a predictable, symmetrical, and repeating dip in the star's light, a tiny, periodic blink. But the data from Tabby's star was anything but predictable. It showed dimming events that were utterly chaotic. There were slight, flickering dips, and then there were colossal drops in brightness, with one event in particular causing the star to dim by a staggering 22%. To put that in perspective, a Jupiter-sized planet would block only about 1% of a sun-like star's light. This was something else entirely. This was as if a vast, irregular swarm of objects covering an area 20 times wider than our own star was passing in front of it, and it was happening with no clear, repeating pattern. Scientists rushed to propose natural explanations, each one pushing the boundaries of known astrophysics. The leading theory involves a massive, uneven cloud of dust and debris, perhaps from a recently shattered planet or a colossal collision between asteroids. This could account for the irregular dimming as different densities of dust pass in front of the star. Another compelling idea points to a family of exocomets, thousands of them, on long, elliptical orbits that occasionally swarm in front of the star, their long tails of gas and dust blotting out its light. These are both fantastic scenarios, painting a picture of a violent, dynamic solar system unlike anything we have nearby. But it was the more speculative explanation that truly captured the public's imagination, the alien megastructure hypothesis. The notion was first raised seriously in a scientific paper, suggesting that the irregular, massive dimming could be consistent with a partially constructed Dyson sphere, a hypothetical swarm of giant energy-collecting panels built by an advanced civilization to harness the entire power output of their star. Imagine an array of solar panels, but on a scale so immense it beggars belief. A vast, intricate network that would be the ultimate signature of a Type 2 civilization on the Kardashev scale. Artist conceptions of such a structure show geometric shapes and strange patterns eclipsing the star, a vision of technology so advanced it looks like magic. Yet, as enthralling as this idea is, the scientific process has slowly begun to lean away from it. Follow-up observations, particularly those measuring the dimming at different wavelengths of light, provided a crucial clue. When a solid object like a megastructure blocks a star's light, it blocks all wavelengths equally, but when dust is the culprit, it blocks more blue light than red light. The data from Tabby's star clearly showed this characteristic filtering, strongly suggesting that whatever is blocking the light is made of tiny particles, not solid panels. The most likely culprit appears to be a colossal cloud of fine, circumstellar dust, perhaps trapped in a complex gravitational dance with the star itself. So has the mystery been solved? Not entirely. While dust seems to be the primary actor, the ultimate source of that dust remains a puzzle. What event could have created such an enormous and dynamic cloud? The star continues to be monitored, and it continues to surprise us with new, less dramatic but still inexplicable flickers. Tabby's star, therefore, defies logic not necessarily because of aliens, but because it presents us with a natural phenomenon that is extreme, rare, and poorly understood. It is a powerful reminder that the universe is a laboratory of immense possibility, capable of producing wonders that we have not yet even thought to look for. It taught astronomers to be open to the wildest ideas because sometimes the truth, even if it's just cosmic dust, can be stranger than fiction. Yet even as we gather these tantalizing clues and signals from the cosmos, we are confronted with a profound and unsettling silence that forms one of the greatest logical contradictions in all of science. We have every reason to believe the universe should be teeming with life. Our own Milky Way galaxy contains hundreds of billions of stars, and many of these are now known to host planets. In fact, current estimates suggest there are more planets in our galaxy than there are stars. With so many worlds, and with the fundamental ingredients for life seemingly common throughout the cosmos, the stage appears to be perfectly set for a grand cosmic community. So where is everybody? This compelling question lies at the heart of the Fermi Paradox, a mystery that has puzzled scientists and philosophers for decades. The paradox gets its name from a casual lunchtime conversation in the summer of 1950. Physicist Enrico Fermi, while discussing recent reports of flying saucers with colleagues, is famously said to have blurted out, "But where is everybody?" His point was brutally simple. If intelligent life is common, then even if only a tiny fraction of civilizations develop the technology for interstellar travel, the galaxy should have been completely colonized by now. Given the age of the galaxy, over 13 billion years, even a civilization moving at a small fraction of the speed of light could have explored or settled every corner of the Milky Way many times over. The Earth itself is a relatively young planet, so why hadn't someone else arrived here long before we even existed? The sheer scale of time and space makes the absence of any visitors or any unmistakable evidence of their existence utterly baffling. To better frame this question, astronomer Frank Drake formulated his famous equation, not to provide a single answer, but to identify all the variables we need to consider. The Drake equation attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. It starts with the number of stars formed each year, then multiplies that by the fraction of stars that have planets, the number of planets per star that can potentially support life, the fraction of those where life actually appears, the fraction where life becomes intelligent, the fraction that develop technology that releases detectable signs into space, and finally, the length of time civilizations release those detectable signals. When you plug in optimistic numbers, you might get thousands of flourishing civilizations. With more conservative estimates, you might get a number much closer to one just us. The equation beautifully illustrates that the answer to the paradox lies hidden in one or more of these factors being much, much smaller than we hope. This line of thinking leads us directly to the most sobering resolution of the Fermi Paradox, the Great Filter Hypothesis. The idea is that there is some kind of barrier, a monumental challenge or cataclysm, that prevents life from progressing to the stage of interstellar colonization. This filter could exist in our past, meaning we have already somehow overcome a challenge that obliterates almost every other civilization. Perhaps the jump from simple prokaryotic life to complex eukaryotic cells is incredibly rare, taking billions of years to occur by chance. Or maybe the filter is still ahead of us. This is the more frightening possibility. It suggests that every advanced civilization inevitably encounters a self-destructive event like nuclear war, a nanotechnology catastrophe, an engineered pandemic, or the unintended consequences of artificial intelligence that wipes them out before they can spread to the stars. Our failure to find others would then be an ominous warning sign of what may yet await humanity. Not all solutions to the paradox are quite so dire, some are wonderfully strange. The zoo hypothesis proposes that extraterrestrial civilizations are indeed out there and are aware of us, but they have deliberately chosen to avoid open contact, placing Earth in a kind of cosmic wildlife preserve. They are observing us from a distance, allowing our civilization to develop naturally without interference, perhaps until we reach a certain level of maturity or wisdom. Another idea is that we are simply looking for the wrong things. Our searchers assume aliens will communicate using radio waves, but a truly advanced civilization might use a technology we haven't even dreamed of yet, like neutrino communication or something beyond our current understanding of physics. It's like trying to detect a smartphone with a telegraph receiver. We might be technologically deaf to their conversations. Perhaps the universe is just too big and the timescales too vast. Civilizations might bloom and fade like fireflies in the night, their signals crossing the immense interstellar distances long after they have gone silent. Or maybe we are, in fact, the first. We could be living in a young universe that is only now becoming habitable, and we are among the pioneers, the first form of intelligent life to look up at the stars and wonder if we are alone. The Fermi Paradox holds no answers, only possibilities. It is not a problem to be solved so much as a profound question to be contemplated, a mirror that reflects our own hopes, fears, and ultimate place in a cosmos that remains stubbornly and mysteriously silent. But the silence of the cosmos and the paradox it presents is built upon a foundation we thought we understood the matter we can see. Yet, as we've pushed our observations further, we've been forced to accept a truth far more bizarre. Most of the universe is made of stuff we cannot see. We have been like children on a beach, studying the intricate patterns of the sand and the foam of the waves, completely unaware that we are standing on the shore of a vast, dark, and invisible ocean. This ocean is dark matter, and its discovery began not with seeing something new, but with realizing that what we could see was behaving in a way that made absolutely no sense. The story starts in the 1930s with a brilliant and stubborn astronomer named Fritz Zwicky. While studying the Coma Cluster, a massive group of galaxies, he made a simple calculation based on the observed motions of its members. The galaxies were whipping around far too quickly. According to the laws of gravity, the tremendous speed of these galaxies should have flung them apart, sending them flying off into the void. The only thing holding the cluster together was the gravitational pull of all the matter inside it. But when Zwicky added up all the matter he could see, the stars, the gas, the dust, it was nowhere near enough to generate the gravity required. It was like watching a dozen twigs tied together with a single thread spinning rapidly without flying apart. The thread simply shouldn't have been strong enough. Zwicky concluded there must be a huge amount of invisible matter providing the missing gravity, and he gave it a name, Dunkel Materie, or dark matter. At the time, most of his colleagues dismissed the idea as outlandish. The concept was resurrected decades later by astronomer Vera Rubin, who faced a similar but more intimate problem. She was meticulously mapping the rotation curves of individual spiral galaxies. We expect stars at the outer edges of a galaxy, far from the bright central bulge, to orbit more slowly than those near the center, just as Pluto orbits our Sun much more slowly than Mercury. But Rubin's data revealed something astonishing. The stars at the very outskirts of galaxies were moving just as fast as those near the core. The galaxies were rotating so quickly that they should have torn themselves apart long ago. The only possible explanation was that each galaxy was embedded within a massive, spherical halo of some unseen material, a halo that provided the extra gravitational glue to hold everything together. This invisible halo had to contain 5 to 10 times more mass than all the visible stars, gas and dust combined. The evidence was undeniable. Dark matter was real. But what is it? We know it exists because we can see its gravitational effects everywhere we look. We see it bending the light from distant galaxies through a process called gravitational lensing, where the immense mass of a dark matter halo acts as a cosmic magnifying glass, warping the fabric of spacetime itself to distort and multiply the images of objects behind it. We see its gravitational fingerprint in the delicate patterns of the cosmic microwave background, the afterglow of the Big Bang. The universe's very structure, the great cosmic web of filaments and voids, was woven by dark matter's gravity, which acted as a scaffolding upon which normal matter could eventually coalesce into galaxies. We know it makes up about 27% of the universe, while the ordinary matter that makes up you, me, planets and stars constitutes less than 5%. The rest is the even more mysterious dark energy, and yet, despite knowing it's there and that it is the dominant form of matter, we have no idea what it's made of. For decades, the leading candidate has been a hypothetical type of particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy, and as their name suggests, they would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. This is why they are so elusive. Billions of these particles might be passing through your body every second without a single interaction. Scientists have built exquisitely sensitive detectors, often placed deep underground in old mines to shield them from cosmic rays, hoping to catch the rare, faint ping of a dark matter particle bumping into an atom of normal matter. So far, after decades of searching, these detectors have heard nothing but silence. This failure to detect dark matter directly has led to other, even more exotic theories. Perhaps dark matter is not a particle at all, but a manifestation of something wrong with our understanding of gravity on the largest scales. This idea, known as modified Newtonian dynamics or MND, proposes that gravity behaves differently when it becomes incredibly weak, like at the edges of galaxies, than Isaac Newton or Albert Einstein predicted. While MND can explain some galactic rotation curves, it struggles to account for all the gravitational evidence we see in colliding galaxy clusters, where the dark matter and the normal matter can be clearly separated. When clusters like the Bullet cluster collide, the visible gas clouds smash into each other and slow down, but the dark matter, which doesn't interact, simply sails right through. The gravitational lensing effect shows that most of the mass is in these regions where there is no visible matter, a result that is very difficult for modified gravity theories to explain. So we are left in a truly peculiar situation. We are surrounded by, and in fact mostly made of, nothing. Not empty space, but a substance that defines the cosmic architecture, dictates the motion of galaxies, and holds the fate of the universe in its grasp, yet remains completely invisible and undetectable by any means other than its ghostly gravitational pull. It is the ultimate cosmic phantom, a reminder that the universe is under no obligation to make sense to us. We have mapped its influence across the heavens, we have built our cosmology upon its existence, and yet its true nature remains one of the most profound and humbling mysteries in all of modern physics. And so we arrive at a mystery that is, in many ways, even more profound and unsettling than dark matter. For if dark matter is the invisible skeleton holding the cosmos together, then our next discovery is the phantom force actively and relentlessly tearing it apart. This force is dark energy, and its discovery was so shocking, so completely contrary to everything astronomers expected, that it sent a seismic tremor through the very foundations of physics, rewriting the future of the entire universe. To understand just how radical this discovery was, we have to rewind to the prevailing view of the cosmos in the late 1990s. The dominant theory, supported by no less a figure than Albert Einstein himself, was that the universe was expanding, a consequence of the Big Bang, but that this expansion should be slowing down. The reason for this is simple and logical: gravity. Every single bit of matter in the universe, from the smallest grain of dust to the largest galaxy cluster, exerts a gravitational pull on every other bit. It was assumed that this collective gravity, this cosmic tug-of-war, would act as a brake on the initial explosive force of the Big Bang. The central question for cosmologists was not if the expansion was slowing, but by how much. Would there be enough matter to eventually halt the expansion and cause the universe to collapse in a big crunch? Or would it just keep expanding forever, slowly coasting toward a cold and distant fade-out? Two rival teams of scientists, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure this deceleration by using a very specific kind of stellar explosion as a cosmic mile marker. They needed a standard candle, an object of known intrinsic brightness, so that by measuring how dim it appeared from Earth, they could accurately calculate its distance. They chose Type 1, a supernova. These are the spectacular deaths of white dwarf stars that have siphoned off too much material from a companion star. Because they all explode at roughly the same mass, they all shine with a very similar peak brightness, making them perfect for measuring vast intergalactic distances. The teams painstakingly searched for these supernovae in incredibly distant galaxies, billions of light years away. By measuring both the distance and the redshift of the light from these explosions, which tells us how much the universe has stretched since the light began its journey, they could map the expansion history of the cosmos. They expected to see that the more distant supernova, whose light was emitted longer ago, would show that the expansion was faster in the past and has been slowing down ever since. But the data told a completely different and frankly unbelievable story. The distant supernova were significantly fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible conclusion was that the expansion of the universe wasn't slowing down at all. In fact, it was speeding up. Some mysterious, repulsive force was actively pushing galaxies apart from one another, overpowering the collective gravitational pull of all the matter in the cosmos. The implications of this discovery were staggering, earning the team leaders the Nobel Prize in Physics in 2011. It meant that the universe is not just expanding, it is accelerating into a future of increasing isolation and darkness. This mysterious force causing the acceleration was dubbed dark energy, and it is now calculated to make up a whopping 68% of the entire mass energy content of the universe. To put that into perspective, dark energy is more than twice as abundant as dark matter, and over 15 times more prevalent than all the normal matter every star, planet, and human put together. It is the dominant component of reality, and we have no idea what it is. The leading theoretical candidate is something that Einstein himself proposed and then later rejected as his biggest blunder. He called it the cosmological constant, a property of empty space itself that exerts a negative pressure, causing spacetime to expand. In this view, the vacuum of space is not truly empty. It is seething with a faint, ubiquitous energy that is literally built into the fabric of the universe. The problem is when physicists try to calculate the strength of this vacuum energy using quantum mechanics, their predictions are off by a factor of 10 to the power of 120. That is a number so unimaginably large it is often called the worst prediction in the history of physics. Other theories suggest dark energy is not a constant but a dynamic field that has changed over time, a concept sometimes referred to as quintessence. Or perhaps it signals a fundamental flaw in our understanding of gravity, requiring a new theory that goes beyond Einstein's general relativity on the largest scales. Whatever its true nature, dark energy is the ultimate puppet master dictating the ultimate fate of everything. It points toward a cold, lonely end for the cosmos, a heat death, or big freeze, where the acceleration continues until galaxies are pushed beyond one another's observable horizons, and the universe becomes an ever-expanding, infinitely dark and profoundly empty void. It is a force of cosmic isolation, and its discovery reminds us that the universe is not only stranger than we imagine, but stranger than we can imagine. But just as we begin to accept this grand, accelerating fate dictated by dark energy, our most detailed map of the infant universe reveals an anomaly so strange, so seemingly impossible, that it threatens to undermine the very cosmological principles upon which our entire modern understanding is built. This is not a force or a particle, but a direction, a preferred axis in the cosmos that, according to all our theories, should not exist. Astronomers, with a mix of dread and fascination, have nicknamed it the axis of evil. To understand why this axis is so evil, we have to go back to the very beginning, to the oldest light we can see, the cosmic microwave background, or CMB. This is the faint, cold afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old, a time when it had cooled enough for the first atoms to form and light to finally travel freely through space. For decades, the study of this primordial radiation has been the cornerstone of modern cosmology. The tiny, random fluctuations in its temperature, warmer and cooler spots just millionths of a degree apart, represent the seeds of all future structure. From these minute density variations, driven by quantum fluctuations stretched to cosmic size during inflation, gravity would eventually pull together the first galaxies and clusters. The standard model of cosmology, known as the lambda cold dark matter model, is built upon the foundation that these fluctuations should be, for the most part, random and evenly distributed across the sky. The universe should have no preferred direction. It should be statistically isotropic, meaning it looks the same in every direction. This is where the plot thickens. When scientists began creating incredibly precise full sky maps of the CMB with satellites like WMAP and later Planck, they noticed something hauntingly peculiar. Some of the largest scale fluctuations, the biggest waves in the fabric of spacetime, appeared to be subtly aligned with each other, and even more bizarrely, they seemed to be aligned with the plane of our solar system. This is the axis of evil. It's as if the universe's blueprint has a faint but undeniable arrow pointing in a specific direction, and that direction just happens to be eerily connected to our own little corner of space. From the viewpoint of the cosmological principle, this is utter heresy. Our location in the universe is supposed to be utterly mundane and unimportant. There should be no special relationship between the structure of the entire cosmos and our local solar system. The name itself, coined by cosmologist Joe Megiddo, is intentionally provocative. It's not that the alignment is sinister, but that its existence is so philosophically inconvenient for our standard models that it feels like a malicious trick. The implications are profound. If this alignment is real and not a statistical fluke or a measurement error, it suggests one of two terrifying possibilities. First, it could mean that we are, in fact, at the center of the universe in some way, a throwback to the pre-Copernican idea that we occupy a special place, a notion that science has spent centuries dismantling. The second, and perhaps more palatable, possibility is that there is something fundamentally wrong or incomplete with our understanding of the inflationary Big Bang model. Perhaps the process of inflation did not create a perfectly uniform universe, but left behind a faint directional imprint, a cosmic grain like that in a piece of wood. Naturally, the scientific community has scrutinized this result with extreme skepticism. The primary suspect is always systematic error. Could the alignment be an artifact of how the data is processed? Perhaps the way we subtract the foreground glow of our own galaxy is inadvertently creating this pattern. Maybe the instruments themselves have some unknown bias. However, after years of analysis and the arrival of even higher precision data from the Planck satellite, the anomaly has stubbornly refused to go away. It persists, a faint but persistent whisper in the data that we cannot seem to explain away. This leaves scientists facing a stark choice. Either we accept that this is the most unbelievable coincidence in the history of science, a chance alignment of the entire universe with our insignificant solar system, or we begin to entertain theories that were once considered fringe. Some have proposed that this could be evidence of a pre-Big Bang universe, a structure that existed before our own cosmos and whose influence bled through. Others suggest it might be a sign that our universe is not alone, that it collided with another universe in the multiverse, leaving a bruise on the sky. The axis of evil remains an unsolved problem, a cosmic cold case that challenges our deepest assumptions about the universe's uniformity and our place within it. It is a humbling reminder that for every answer we find, the cosmos seems to have a deeper, more perplexing question waiting in the wings. And just as we grapple with the cosmic scale enigma of the axis of evil, our next discovery pulls us into the bizarre and counterintuitive realm of the very small, a realm where the laws of physics operate in ways that seem to defy the very nature of reality itself. This phenomenon is so strange that even Albert Einstein himself was deeply troubled by it, famously dismissing it as spooky action at a distance. Today, we know it as quantum entanglement, and its implications are so profound that they ripple all the way out to the farthest reaches of the cosmos, connecting the fabric of space in ways we are only beginning to comprehend. At its heart, quantum entanglement is a simple concept with mind-bending consequences. It occurs when two particles, like photons or electrons, are created or interact in such a way that their properties become inextricably linked, forming a single, unified quantum system. From that moment on, no matter how far apart you separate them, whether it's across a lab bench or across the galaxy, they cease to be independent objects. Measuring a property of one particle, such as its spin or polarization, will instantly determine the corresponding property of its partner. This connection is immediate, seemingly faster than the speed of light, and it appears to violate a fundamental rule of Einstein's theory of relativity, which states that no information or influence can travel faster than light. This was the source of Einstein's frustration. It looked like a cosmic cheat code. For decades, this remained a fascinating philosophical puzzle debated in thought experiments. The central question was whether the particles contained hidden, predetermined information about their states all along, an idea known as local hidden variables. But in the 1960s, physicist John Bell devised a brilliant theoretical test, now known as a Bell test experiment, that could determine once and for all whether this spooky action was real or if there was a simpler, more classical explanation. The experiment involves measuring the correlations between the entangled particles along different angles. If local hidden variables were true, the correlations would never exceed a certain limit. But if quantum mechanics was correct and the particles were truly connected in a spooky way, the correlations would be stronger. For years, carrying out a truly airtight Bell test was impossible because of potential loopholes, like the possibility that the particles could be communicating through some unknown channel or that the detectors were inefficient. This is where our journey to the stars comes in. To finally close these loopholes and settle the debate, scientists realized they needed to separate the particles by such a vast distance that any signal between them, even traveling at the speed of light, would not have enough time to communicate before the measurement was complete. And the best way to achieve this enormous separation was to leave Earth behind. In 2017, a team of Chinese scientists conducted a landmark experiment using a satellite called MISHUS. They created pairs of entangled photons on the satellite and then beamed each member of the pair down to 2 different ground stations in China, separated by over 1,200 kilometers. As these photons traveled through the vacuum of space to their respective detectors, the distance between them was so vast that any hypothetical faster-than-light signal would have needed thousands of times longer to travel between the stations than the entire measurement process took. The results were unequivocal. The correlations between the photons violated Bell's limit dramatically, providing the most definitive proof yet that quantum entanglement is real and that this spooky action is a genuine feature of our universe. So what does this mean for our understanding of reality? The most straightforward interpretation is that the universe is fundamentally non-local. The properties of a particle are not necessarily defined until they are measured, and the act of measurement itself on one side of the universe instantly influences the state of its partner with no travel time in between. This suggests that at a deep quantum level, the concepts of space and separation might be an illusion. Entangled particles do not exist in 2 different places. In a very real sense, they occupy a single quantum state that transcends the physical distance between them. It's as if the universe is woven together with invisible threads that ignore the vast emptiness of space. This has staggering implications not just for philosophy, but for the future of technology. This same principle of quantum entanglement is the foundation for emerging fields like quantum computing and quantum cryptography. A quantum internet, for instance, could use entangled particles to create communication links that are utterly unhackable, because any attempt to eavesdrop on the particles would immediately disrupt their delicate entangled state, alerting the users to the breach. We are starting to harness this spookiness to build a new generation of technology that operates on the fundamental laws of the quantum world. The experiments conducted from space have not only confirmed one of the weirdest predictions of quantum mechanics, but have also opened a door to a future where the universe's most bizarre behavior becomes the bedrock of our technological civilization. But this strange connection between particles across vast distances is not the only time our spacecraft have sent back data that defied simple explanation. Sometimes the mystery was baked into the very trajectory of our robotic explorers, a tiny, persistent nudge that refused to go away. This brings us to the curious case of the Pioneer probes and a puzzle that plagued NASA scientists for decades, the Pioneer anomaly. Launched in the early 1970s, Pioneer 10 and Pioneer 11 were true trailblazers. Their missions were audacious: to be the first human-made objects to travel through the asteroid belt, swing by Jupiter and Saturn, and then just keep going, sailing on into the infinite dark beyond our solar system. For years, they dutifully phoned home, their faint signals tracked with exquisite precision by the Deep Space Network. But as they ventured farther from the Sun, navigators began to notice something peculiar in the Doppler data of their radio signals. Both spacecraft were experiencing a tiny, unexplained acceleration back toward the Sun. It was as if a faint, invisible hand was gently tugging on them, slowing their exit into interstellar space. This deceleration was minuscule, about 10 billion times weaker than the gravity we feel on Earth, but it was constant, unidirectional, and most importantly, it wasn't predicted by any of our models of the solar system. The immediate suspicion, of course, was that we simply didn't understand the gravity in the outer solar system. Was there a hidden source of mass out there, a previously unknown planet, a belt of dark matter, or maybe even the gravitational effects of a small black hole? Others looked to more exotic physics, suggesting this could be the first observational evidence that Einstein's theory of general relativity needed a slight modification on very large scales. Perhaps the pull of gravity behaved differently over such immense interplanetary distances. For a time, the Pioneer anomaly became a beacon for those hoping to find a crack in our standard model of physics, a hint of something new and revolutionary. The solution, however, turned out to be far more mundane, yet in its own way brilliant. It wasn't a flaw in our understanding of the cosmos, but a subtle and overlooked detail in the engineering of the spacecraft themselves. The Pioneers were powered by radioactive thermoelectric generators, and these units generated a significant amount of heat. That heat had to be radiated away into space to keep the craft's electronics from frying. The spacecraft were designed with a specific geometry. Heat was emitted from the sides of the craft, but more importantly, it was also radiated from the main dish antenna, which was pointed back toward Earth and therefore back toward the Sun. This created a tiny but constant photon thrust. Think of it like a very, very weak rocket engine. Every photon of heat radiating from the front of the spacecraft gave it an imperceptible push in the opposite direction, back toward the Sun. Proving this was a Herculean task of digital archaeology. The original engineers had long since retired, and much of the design data was stored on archaic formats. A dedicated team spent years painstakingly reconstructing the thermal model of the Pioneer spacecraft, accounting for every watt of power generated by the onboard systems and tracing the complex paths that heat would have taken as it radiated away. They even had to account for the slow decay of the plutonium power source, which meant the heat output, and thus the anomalous thrust, was decreasing over time. When they finally ran the complete simulation, the numbers matched almost perfectly. The phantom acceleration was real, but its source was not some new law of physics. It was the gentle, relentless push of photons from the spacecraft's own warmth. The resolution of the Pioneer anomaly is a powerful lesson in scientific humility. It reminds us that before we can declare a revolution in physics, we must first be certain we have accounted for every last mundane detail in our own backyard, or in this case, on our own spacecraft. It was a triumph not of discovering something new about the universe, but of rediscovering something we had built ourselves, a hidden signature of our own ingenuity that we had temporarily mistaken for a message from the cosmos. Yet even as we solve one mystery close to home, the universe is more than capable of sending us new ones from unimaginable distances, and few are as explosive, fleeting, and utterly perplexing as the phenomenon of fast radio bursts. Picture this, a single, blindingly intense pulse of radio waves, a cosmic shout that compresses more energy than our Sun puts out in 80 years into a mere millisecond. And then, just as suddenly as it arrived, it's gone. For years, these events were the ghosts of radio astronomy, so brief and unpredictable that many astronomers doubted their extraterrestrial origin at all, wondering if they were merely glitches in our own equipment. But the evidence became undeniable. These bursts are real, they are coming from deep space, and their origins are one of the most active and exciting frontiers in modern astrophysics. The story of their discovery begins in 2007, when astronomer Duncan Lorimer was sifting through archived data from the Parkes radio telescope in Australia, looking for new pulsars. Buried in the observations was a signal so strong and so isolated that it stood out like a scream in a silent library. It became known as the Lorimer burst. The most telling clue was its dispersion, a telltale smearing of the signal across different radio frequencies. Higher frequencies arrived at the telescope a fraction of a second before the lower frequencies. This happens because the waves travel through the sparse plasma of intergalactic space, which slows down the lower frequencies just slightly. The amount of this delay acts as a cosmic odometer. The greater the smear, the more material the signal has passed through, and therefore the farther it has traveled. The dispersion measure of that first burst pointed to a source billions of light-years away, far beyond our own galaxy. This was no local event. This was a message from the deepest cosmos. The mystery only deepened with the discovery that not all FRBs are created equal. Most are one-off events, a single, monstrous explosion that tears across the universe and is never heard from again. But a few are repeaters. They fire off again and again, sometimes in a predictable pattern, sometimes at random, from the exact same patch of sky. This crucial distinction ruled out a whole class of cataclysmic, one-time only explanations. You can't have a second Big Bang from the same location. The existence of repeating FRBs pointed strongly toward a source that could survive the event, some kind of energetic engine that could power multiple colossal outbursts. So what cosmic engine could possibly produce such staggering amounts of energy in such an impossibly short time? The suspect list is as fascinating as it is varied. The prime candidates are magnetars, a type of neutron star with a magnetic field so intense it's beyond human comprehension. A magnetar's magnetic field is a quadrillion times stronger than Earth. It's thought that these stars can experience massive starquakes ruptures in their rigid crust that release titanic shocks, potentially powering these brilliant radio bursts. In a stunning development in 2020, a magnetar within our own galaxy was observed producing an FRB-like burst, providing the first direct evidence linking at least some of these events to these incredible objects. But the universe loves variety, and magnetars may not be the only source. Other theories involve the spectacular mergers of incredibly dense objects, like two neutron stars spiraling into each other or a neutron star being consumed by a black hole. These events release gravitational waves and could potentially unleash a corresponding blast of electromagnetic radiation. Another compelling idea points to a special kind of highly active pulsar, or even the violent eruptions from a young magnetar powering through a thick cloud of debris left over from its supernova birth. And of course, in the absence of a definitive answer, the most thrilling possibility inevitably surfaces. Could these be signals from an advanced extraterrestrial civilization? The idea of an alien beacon is captivating, but most scientists consider it the least likely explanation. The bursts are incredibly broadband, meaning they spread their energy across a wide range of frequencies, which is an extremely inefficient way to communicate. It would be like trying to have a conversation by simultaneously shouting on every radio station on the dial. The amount of energy required to broadcast such a signal across intergalactic distances is almost unimaginable, even for a hypothetical super-civilization. While we can't completely rule it out, the natural explanations, though still mysterious, are far more probable. The real power of fast radio bursts may ultimately lie not just in what they are, but in what they can do for us. Because these signals wash through the invisible matter between galaxies, they act as the perfect probes for the missing baryon problem. Our inventories of normal matter in the nearby universe always come up short. We can account for the matter in stars and galaxies, but a significant portion seems to be missing. It's believed this missing matter exists as a diffuse, hot gas in the spaces between galaxies, but it's incredibly difficult to map. Each FRB, with its unique dispersion signature, gives us a single, precise measurement of the total number of electrons it encountered along its path. By collecting enough of these bursts from all across the sky, astronomers are essentially building a three-dimensional map of the universe's structure, weighing the cosmic web itself one burst at a time. These enigmatic flashes, born from some of the most violent events in the cosmos, may ironically end up being our most delicate tools for illuminating the dark, vast, and empty spaces that connect everything. Yet, even as we use fleeting cosmic flashes to map the universe's hidden matter, a far more persistent and fundamental disagreement has been growing in the background, one that strikes at the very heart of our ability to measure the cosmos. This isn't a mystery about a strange object or a fleeting signal. It's a crisis of consistency. It's the growing and uncomfortable realization that our two most trusted methods for measuring the universe's expansion rate, the Hubble constant, are giving us two different, stubbornly irreconcilable answers. This discrepancy has become so pronounced and so persistent that cosmologists have given it a name that conveys both its gravity and their frustration: the Hubble tension. To understand why this tension is such a big deal, we need to understand what the Hubble constant represents. It's not just any number, it's arguably the most important number in cosmology. The Hubble constant, denoted as h0, measures how fast the universe is expanding at the current time. It tells us how quickly galaxies are receding from us, and by extension, it allows us to calculate the age of the universe, its size, and its ultimate fate. For nearly a century, pinning down this number's exact value has been the holy grail of observational cosmology. The problem is, we now have two golden methods to measure it, and they are fundamentally disagreeing. The first method looks back to the very beginning, to the infant universe. It uses the exquisitely detailed map of the cosmic microwave background, the afterglow of the Big Bang, as captured by the Planck satellite. Scientists take this snapshot of the early universe and run it forward through our incredibly precise standard model of cosmology, the lambda cold dark matter model. This model includes all the ingredients we know about ordinary matter, dark matter, and dark energy. By fine-tuning the model until it perfectly reproduces the patterns we see in the CMB, we can predict what the expansion rate should be today. This is known as the early universe or CMB measurement. The Planck data gives us a very precise value, approximately 67.4 kilometers per second per megaparsec. This means that for every megaparsec, about 3.3 million light-years of distance, a galaxy is moving away from us 67.4 kilometers per second faster. The second method measures the expansion rate directly in our local, modern universe. This is the late universe or distance ladder method. Astronomers use brilliant, reliable standard candles like Type Ia supernova and Cepheid variable stars to measure the distances to nearby galaxies with incredible accuracy. By comparing these precise distances to the redshifts of those same galaxies, which tells us how fast they are moving away from us, they can calculate the Hubble constant directly. Teams using the Hubble Space Telescope and other observatories have refined this method to an astonishing degree of precision, and their answer is consistently and undeniably higher, around 73 kilometers per second per megaparsec. At first glance, a difference of about 5 or 6 units might not seem like much, but in the world of high-precision cosmology, where error bars have shrunk to less than 2%, this gap is a yawning chasm. The discrepancy is now at a level of about 5 sigma, meaning there is only a 1 in a million chance that it's a random statistical fluke. This isn't a small error, it's a direct contradiction. It's as if you used two different, perfectly calibrated rulers to measure the same table and got two different lengths every single time. One ruler, built from the blueprint of the early universe, says the table is one length. The other ruler, made from direct measurement of the modern universe, insists it's another. They can't both be right, so what's going on? The scientific community is fiercely debating two broad possibilities. The first and more conservative explanation is that there is an unaccounted for systematic error in one or both measurements. Perhaps our calibration of the cosmic distance ladder isn't as rock solid as we think. Maybe there is some unknown property of Cepheid variables or supernova that we are misinterpreting. On the CMB side, maybe our understanding of the physics of the early universe is incomplete in a subtle way that throws off the prediction. Teams on both sides have checked and rechecked their work, hunting for any possible error, but the tension refuses to vanish. It has only grown stronger with better data. This leads to the far more exciting possibility that the Hubble tension is real, and it is the first observable evidence that our standard model of cosmology is incomplete. We might need new physics. The lambda CDM model has been spectacularly successful. But what if it's missing an ingredient? Perhaps dark energy isn't a constant but is evolving over time, growing stronger and accelerating the expansion faster than our models predicted. Maybe dark matter has properties we haven't yet discovered, interacting with itself or with normal matter in a way that affects the expansion history. Some theorists have even proposed the existence of a new type of relativistic particle from the early universe, like a new kind of neutrino that would change how we calculate the CMB's prediction. The implications are staggering. Confirming that the Hubble tension requires new physics would be the most significant shake-up in cosmology since the discovery of dark energy itself. It would force us to rewrite our textbooks on the fundamental components and evolution of the universe. We are essentially being presented with a cosmic puzzle, a clue left for us by the universe that our current understanding, as successful as it has been, is only an approximation of a deeper, more complex reality. The Hubble tension is not just a technical disagreement between datasets, it is a potential doorway to a new chapter in physics, a sign that the cosmos still holds profound secrets about its own inner workings. Just when we thought the outer solar system was the domain of our own familiar planets and comets, the cosmos delivered a visitor that shattered that notion entirely, a silent, fast-moving messenger from the depths of interstellar space. In October 2017, the Pan-STARRS telescope in Hawaii detected a faint point of light moving at breathtaking speed. Its trajectory was immediately recognized as hyperbolic, meaning it was not bound by the sun's gravity. This was no asteroid from our backyard. It was the first object ever seen from another star system, and it was already on its way out. Astronomers named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, and it would quickly become one of the most debated cosmic discoveries of the century. What made Oumuamua so extraordinary wasn't just its origin, but its bizarre characteristics. As telescopes around the world swiveled to track it during its brief flyby, they captured a light curve with extreme variations in brightness. This suggested the object was tumbling end over end, and its drastic changes in luminosity implied an incredibly elongated shape. Something like a pancake or a cigar, with estimates suggesting it was up to 10 times longer than it was wide. This was unlike any asteroid or comet we had ever seen in our own solar system, where objects tend to be more lumpy and rounded. But the biggest mystery emerged when astronomers analyzed its path with precision. Oumuamua wasn't just following a purely gravitational trajectory as it raced away from the sun. It was accelerating ever so slightly, as if it had a tiny engine of its own. This non-gravitational acceleration is the detail that launched 1,000 theories. For comets in our solar system, such acceleration is common and is caused by outgassing. As a comet approaches the sun, its icy surface heats up, releasing jets of gas and dust that act like a natural thruster. But here was the problem. Despite intense scrutiny, Oumuamua showed absolutely no visible signs of this activity. No coma of gas, no tail of dust, nothing. It was as dark and inert as a rock, yet it was clearly pushing itself along. This paradox acceleration without a visible cause is what fueled intense speculation, including the provocative suggestion by Harvard astronomer Avi Loeb that we might be looking at a piece of alien technology, perhaps a light sail or a derelict probe from another civilization. The scientific community, while fascinated by the possibility, largely sought natural explanations, and over time a compelling one has emerged. The leading hypothesis is that Oumuamua is a cosmic iceberg composed largely of molecular hydrogen. Hydrogen is the most common element in the universe, but it's notoriously difficult to see. A block of solid hydrogen ice would be virtually invisible to our telescopes, yet as it passed close to the sun, the heat could have caused the hydrogen to sublimate directly from solid to gas. This invisible outgassing would provide just the right amount of thrust to explain the observed acceleration, all without producing a visible dusty tail. This theory paints a picture of Oumuamua as a fragile relic from the birth of another solar system, a chunk of a Pluto-like planet that was shorn off billions of years ago and has been drifting in the freezing void of interstellar space ever since, its structure slowly annealed by cosmic rays into that strange, flattened shape. Whether it was an exotic hydrogen iceberg or something even more unusual, Oumuamua's brief passage was a monumental event. It served as tangible proof that interstellar objects are constantly passing through our solar system, a fact confirmed just a few years later with the arrival of the more comet-like Borisov. This scout from a distant star didn't stop to answer our questions, but it delivered a powerful message. The galaxy is dynamic and full of material moving between stars, and our solar system is not an isolated island. It is part of a vast, interconnected ecosystem, and we are only just beginning to learn how to read its messages. But if the mysteries of visitors from other stars and the tension in our cosmic measurements challenge our understanding of the universe's structure, our next discovery threatens the very foundations of physics itself. It is a paradox so profound that it questions whether reality can preserve its own history, and it forces a confrontation between the two most successful theories ever devised by the human mind. This is the black hole information paradox, and it begins with a seemingly simple question with an impossible answer. When something falls into a black hole, is the information about what it was truly lost forever? To understand the stakes, we need to grasp a fundamental rule of the quantum universe. In the everyday world, if you burn a book, it seems the information is destroyed. But in principle, if you could collect every single ash particle, every wisp of smoke, and measure the precise heat radiated, you could theoretically reverse the process and reconstruct the book. Quantum mechanics insists that information cannot be truly destroyed. It can only be scrambled, hidden, or transformed. This principle of unitarity is the bedrock of quantum theory, ensuring the past always leaves a recoverable trace. Now enter the black hole, the ultimate cosmic shredder, as described by Einstein's theory of general relativity. Its event horizon is a point of no return. Once matter crosses this boundary, it is irretrievably lost to the universe, destined to be crushed into the infinitely dense singularity at the center. For decades, physicists accepted this grim fate. Then, in the 1970s, Stephen Hawking performed a stunning calculation that merged quantum theory with gravity just outside the black hole's horizon. He discovered that black holes are not completely black. Due to quantum fluctuations, they slowly emit a faint glow of radiation, now famously known as Hawking radiation. This radiation is thermal, meaning it is completely random and featureless, like the heat from a stove. It contains no information whatsoever about the intricate details of the stars, planets, or books that fell in. This creates the paradox. As the black hole radiates, it loses mass and eventually evaporates completely, vanishing from the universe. If the Hawking radiation is purely thermal and random, then all the information about everything it ever consumed has been erased from existence. The universe's quantum rulebook has been violated. The information is gone. This conclusion was so unsettling that Hawking himself initially believed it meant quantum mechanics had to be revised. It sparked a decades-long debate, famously symbolized by a bet between Hawking and physicist John Preskill, who wagered that information must somehow be preserved. For years, the prevailing, if unsatisfying, solution was the no-hair theorem, which suggested black holes could be described by only three properties: mass, electric charge, and spin. All other details, all the hair that made an object unique, were shaved off at the event horizon and lost. A black hole formed from a collapsed star and one formed from a collection of antique dictionaries would be perfectly identical. This idea preserved the purity of general relativity but utterly demolished the principle of quantum information conservation. the debate intensified with the proposal of an even more radical idea, the black hole firewall paradox. If information is to be preserved as quantum mechanics demands, then the event horizon cannot be the smooth, gentle space that general relativity describes. Instead, it might be a seething, violent wall of incredibly high-energy particles, a literal firewall that would incinerate anything crossing it. This would resolve the information paradox by effectively encoding the data of infalling matter onto this energetic barrier, but it would create a new crisis by violating Einstein's equivalence principle, which states that an observer falling into a black hole should experience nothing unusual at the horizon. You simply cannot have both a smooth space-time and preserved information. The two most fundamental theories of physics were now at war. The path toward a potential resolution began to emerge from a startling discovery about the nature of the event horizon itself. It may not be the sharp, two-dimensional boundary we often imagine. Quantum effects suggest it could be a fuzzy, extended region, a phenomenon sometimes called a quantum atmosphere around the black hole. In this view, the information of infalling matter isn't lost at the singularity, but is somehow imprinted or encoded onto this horizon itself in unimaginably tiny Planck-scale units. As the black hole evaporates via Hawking radiation, this radiation isn't completely random after all. It interacts with this encoded information in extremely subtle ways, carrying it away bit by bit like a slow cosmic data stream. The information isn't destroyed, it is returned to the universe in a vastly scrambled but theoretically recoverable form. This idea aligns with the holographic principle, which suggests that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, much like a hologram on a credit card. The surface area of the event horizon could contain all the information about everything within the black hole. Recent developments have provided tantalizing support for this view. In 2019, a team of researchers calculated that the entropy of a black hole, a measure of its information content, creates a repulsive force that physically prevents the formation of a true singularity, potentially avoiding the information-destroying endpoint. Other work in string theory and quantum gravity continues to find mechanisms where information can leak back out. In 2023, Stephen Hawking's final collaborator on this topic, Malcolm Perry, suggested that black holes may possess a quantum attribute called soft hair, zero-energy particles that ring the horizon and can store information about what fell in. While the complete solution remains one of the holy grails of theoretical physics, the consensus has dramatically shifted. Most physicists now believe that information is, in fact, preserved. Hawking himself conceded the bet to Preskill in 2004, presenting him with an encyclopedia of baseball, from which information can be recovered at will. The universe, it seems, does keep a receipt. It just files it away in the most bizarre and counterintuitive filing system imaginable, ensuring that not even the darkest depths of a black hole can truly erase the story of what came before. But our cosmic neighborhood holds mysteries far closer than interstellar visitors or evaporating black holes, mysteries that have played out in plain sight on the desolate surface of our own moon. For centuries, astronomers using everything from the naked eye to the most powerful telescopes have documented strange, fleeting lights on the lunar surface, sudden flashes, unexplained glows, and shifting obscurations that appear and vanish without warning. These events are known as transient lunar phenomena, or TLP, and they represent one of the most enduring and frustrating puzzles in observational astronomy, a mystery that persists literally right on our celestial doorstep. The historical record is filled with these enigmatic accounts. As far back as the year 1178, a group of English monks reported witnessing a flaming torch on the moon, a spectacle that ended with sparks and a blackening of the surface. In the 18th century, the renowned astronomer Sir William Herschel, the discoverer of Uranus, observed several bright red spots on the lunar surface during an eclipse, which he believed to be evidence of active lunar volcanoes. These weren't isolated incidents. Over 1,000 such events have been logged by credible observers, all describing similar brief anomalies, pinpoint flashes of light, amorphous-colored hazes that linger in craters, or patches of landscape that suddenly become blurred or dimmed as if veiled by a transient fog. For a world we consider to be geologically dead and utterly airless, this activity is profoundly strange. The challenge with TLP has always been their fleeting and unpredictable nature. Unlike tracking a distant galaxy, you can't simply point a telescope at the moon and wait for a flash. It requires immense patience and a great deal of luck. This unpredictability has made systematic study incredibly difficult, often relegating reports to the status of intriguing anecdotes rather than solid data. Were these observers simply tricked by Earth's turbulent atmosphere, or were they seeing something real happening 250,000 miles away? The advent of modern photography and, later, continuous video monitoring from dedicated amateur networks and professional observatories has finally begun to provide the evidence needed to take TLP seriously. We now have high-quality footage capturing these very events, brilliant flashes against the gray lunar soil, undeniable proof that something is causing these bursts of light. So what could possibly be energizing the lunar surface? Scientists have proposed a range of explanations, each fascinating in its own right. The most straightforward cause is meteoroid impact. The moon lacks a protective atmosphere, so even small pebbles from space strike its surface at tremendous speeds, instantly vaporizing on impact and creating a brief, hot flash of light. NASA has programs that actively monitor these impacts, and they are a constant and predictable occurrence, especially during known meteor showers. However, while impacts can explain many sudden flashes, they don't account for the slower, lingering glows or the obscurations that can last for minutes or even hours. This leads to the second major theory, outgassing. The idea is that trapped radioactive gases like radon-222, decaying deep within the moon's interior, could build up pressure until they suddenly rupture the surface and vent into the vacuum of space. As this dust and gas erupts into the sunlight, it could scatter light, creating a temporary, hazy bright spot or a cloud that obscures the terrain below. This would explain the longer duration events and their preference for certain locations, like the edges of Large Maria or the crater Aristarchus, a notorious hotspot for TLP reports. It suggests that the moon might not be entirely geologically dead, but still possesses a faint, simmering internal activity. A more speculative, yet scientifically intriguing, idea involves triboluminescence or electrical phenomena. The moon's surface is constantly bombarded by the solar wind, a stream of charged particles from the sun. It's possible that the resulting electrical charges could build up on the surfaces of dust grains, particularly in areas with specific mineral compositions. A small disturbance, perhaps even a tiny landslide on a crater wall, could trigger a sudden discharge, a miniature lightning bolt, or a flash of static electricity lighting up the lunar night. This would be a completely alien form of geology, a weatherless world still capable of creating its own fleeting electrical storms. Despite these plausible theories, transient lunar phenomena remain poorly understood. Coordinating observations to catch an event in progress with multiple instruments, optical telescopes, spectrometers, and orbital spacecraft is a monumental logistical challenge. We need to analyze the light from a flash to determine its composition and temperature, which would instantly tell us if it was from an impact, a gas release, or something else entirely. Until we can do that consistently, TLP will stay in the realm of mystery. They serve as a powerful reminder that even the most familiar object in our night sky still holds onto its secrets, challenging our assumptions and inviting us to look a little closer at our silent, shining companion. Yet even as we map the grand, uniform tapestry of the cosmic microwave background, One particular feature stands out as a startling blemish, a cold spot so vast and so profound that it seems to defy the very statistical predictions of our best cosmological models. This isn't just a slightly cooler patch, it is a colossal region of space nearly 1 billion light-years across that registers as significantly colder than its surroundings in the universe's oldest light. Its existence is a direct challenge to the idea that the early universe was smooth and random, and it has sparked a fierce debate. Is this the imprint of the largest structure we've ever identified, or could it be something far more extraordinary, a bruise from a collision with another universe? The story of the cold spot's discovery begins with NAS, a Wilkinson Microwave Anisotropy Probe, or WMAP, which produced a detailed full sky map of the CMB in the early 2000s. Astronomers were meticulously analyzing the temperature fluctuations, expecting them to follow a predictable statistical pattern, when they found an anomaly in the constellation Eridanus that was simply too large and too cold to be easily explained by chance. The probability that such a feature could arise randomly in our standard model of the universe was calculated to be less than 2%, making it a significant outlier. This wasn't a mere statistical glitch, it was a genuine cosmic peculiarity that demanded an explanation. The follow-up data from the even more precise Planck satellite only confirmed the cold spot's existence, solidifying its status as one of the most intriguing puzzles in modern cosmology. Scientists initially proposed a compelling, though still fantastic, natural explanation, a supervoid. The theory suggests that this cold region in the CMB might not be a feature of the primordial universe itself, but rather a secondary effect caused by an immense void in the distribution of galaxies between us and the CMB. This concept relies on a phenomenon known as the integrated Sachs-Wolf effect. As light from the CMB travels through the universe, it gains a tiny amount of energy when it falls into a gravitational well, like a cluster of galaxies, and loses energy when it climbs out. However, in a universe dominated by dark energy, which causes the expansion to accelerate, these gravitational wells become shallower over time. This means a photon climbing out of a well loses more energy than it gained falling in, resulting in a net energy loss. If that photon passes through a vast underdense region, a void, where the gravitational pull is weaker, the effect is reversed and the photon experiences a net energy gain. When we observe this, the CMB light that passed through the void appears slightly colder than the average. For the cold spot to be explained this way, the void would need to be truly enormous, perhaps the largest single structure ever identified. The hunt for this proposed supervoid was on. Astronomers began mapping the galaxy distribution in the direction of the cold spot, and some surveys did indeed find evidence of a large, underdense region there. However, there was a major problem. The void they found, while significant, was not nearly large enough or empty enough to account for the profound coldness observed in the CMB. The energy deficit was simply too great. The discovered void could explain perhaps only 10 or 20% of the temperature drop, leaving the vast majority of the cooling a complete mystery. This mismatch between the observed void and the required void created a crisis for the supervoid theory, forcing cosmologists to consider even more radical ideas. This is where the narrative takes a breathtaking turn into the realm of the multiverse. If a mundane structure within our universe cannot explain the cold spot, perhaps its origin lies from outside our universe altogether. The leading alternative hypothesis is that the cold spot is a cosmic bruise, an imprint left by a collision between our universe and another bubble universe in the vast multiverse. The theory of eternal inflation suggests that our universe is just one bubble in a frothing, infinite multiverse, where new universes are constantly budding off, each with their own distinct physical laws. Sometimes these expanding bubbles can collide. If a neighboring universe bumped into ours in the distant past during the inflationary period, the energy released in that collision could have left a distinct signature on the CMB of both universes, a circular patch of anomalously low temperature. The size and profile of the cold spot match the predictions for such an event remarkably well. Of course, this idea is incredibly difficult to prove. A collision with another universe is not exactly a repeatable laboratory experiment. The evidence remains circumstantial, resting on the continued failure to find a sufficiently large void and the intriguing alignment of the cold spot's properties with multiverse theories. The debate between the supervoid and the multiverse collision explanations is a beautiful example of scientific investigation at its most extreme. We are using the subtle patterns in the oldest light in creation to interrogate the possibility of entire other universes. Whether the final answer lies in an unseen expanse of nothingness within our cosmos or a shattering impact from outside of it, the cold spot remains a defiant anomaly. It is a stark reminder that our universe might not be a perfectly isolated system, and that the echoes of its most violent beginnings or its most alien contacts are still written across the sky for us to decipher. And just as we start to think of dark matter as the indispensable cosmic glue holding every galaxy together, the universe presents us with a stunning exception to the rule, a ghostly, see-through galaxy that seems to be missing this invisible ingredient entirely. This is NGC 1052 DF2, and its discovery didn't just add a new type of galaxy to our catalogues. It directly challenged the foundational role we believe dark matter played in the birth of every single island universe. Found lurking near the elliptical galaxy NGC 1052, DF2 is what's known as an ultra-diffuse galaxy. It's about the same size as our Milky Way, but it contains only about 1/200th of the stars, making it incredibly faint and wispy. You could look almost right through it. A team led by astronomer Pieter van Dokkum was studying its globular clusters, bright, dense groups of ancient stars that orbit the galaxy like bees around a hive. The motion of these clusters can be used as a proxy to measure the galaxy's total mass, both visible and dark. By tracking their speeds, astronomers can calculate the gravitational pull holding them in place. In a typical galaxy, these clusters would be zipping around at high speeds, held in check by the immense, unseen mass of a dark matter halo. But when Van Dokkum's team calculated the velocities of DF2's globular clusters, they were stunned. The clusters were moving surprisingly slowly. In fact, their motions could be accounted for entirely by the gravitational pull of the stars they could see. There was no need for any extra invisible mass. The calculated total mass of the galaxy matched the mass of its visible stars almost perfectly. This meant that, unlike every other galaxy ever studied in depth, DF2 appeared to have no dark matter at all. This was a result so counterintuitive that the initial reaction from the broader astronomy community was profound skepticism. It seemed to defy a core tenet of modern cosmology, that dark matter forms the scaffolding upon which all galaxies are built. The discovery immediately sparked a fierce debate centering on two possibilities. The first was that this was simply a monumental error in measurement or interpretation. Perhaps the distance to the galaxy was wrong, which would throw off all the mass calculations. Maybe the globular clusters weren't true tracers of the galaxy's gravitational field, or our viewing angle was somehow misleading us about their true velocities. Critics argued that if the galaxy were much closer to us than initially thought, its stars would be intrinsically dimmer, meaning there would be less visible mass, and the mysterious missing mass would reappear as required dark matter. Subsequent observations, however, including more precise distance measurements from the Hubble Space Telescope, have largely confirmed the original findings. DF2 really is as massive as its stars alone suggest, making it the first convincing example of a galaxy born without a dark matter halo. If the measurement is correct, then we are forced to confront the second, far more exciting possibility, that our understanding of galaxy formation needs a serious revision. How could such a galaxy even exist? One compelling theory suggests it is a failed galaxy. Perhaps it formed from gas that was stripped away from another galaxy during a violent tidal interaction, a cosmic collision that ripped away both gas and dark matter, leaving behind only a trailing stream of stars that eventually coalesced into this ethereal object. In this scenario, DF2 wasn't born without dark matter. It had its dark matter violently stolen, leaving behind a ghostly stellar remnant. Another, even more profound implication is that the existence of a dark matter-free galaxy actually provides indirect evidence for dark matter itself. Think about it. If the phenomenon we've been calling dark matter were actually a sign that our theory of gravity is wrong, as proposed by theories like Embark, then that modified gravity should apply everywhere in every galaxy. There should be no exceptions. The fact that we have galaxies like DF2 that follow the rules of Newtonian gravity perfectly, while the vast majority of others require dark matter to explain their motions, creates a huge problem for modified gravity theories. It suggests that dark matter is indeed a real physical substance that can be present or absent, not just a modification of the laws of physics. In a strange way, a galaxy without dark matter makes the case for dark matter's existence stronger than ever. DF2 is no longer alone. Other dark matter-deficient galaxies have since been tentatively identified, suggesting this might be a rare but genuine class of object in the universe. They stand as cosmic counterexamples, proving that the recipe for a galaxy can, on occasion, leave out its most crucial ingredient. They force us to accept that the universe has more than one way to build a galaxy, and that the dark matter story, while dominant, is not the only tale being told in the vast expanse of space. Now, after exploring ghostly galaxies and cosmic cold spots, we plunge into the heart of the atom itself, where the rules of nuclear binding are being rewritten by a particle that shouldn't exist. We are taught that the atomic nucleus is held together by the strong nuclear force, a powerful glue that binds protons and neutrons, but this force has a peculiar quirk. It seems to despise solitude. A single neutron, all by itself, is unstable and will decay into a proton in a matter of minutes. Even two neutrons alone cannot form a stable bound state. The d-neutron is unbound and fleeting. The very idea of three neutrons forming a nucleus is a non-starter, so you can imagine the profound shockwave that went through the physics community at the possibility of a stable particle made of four neutrons, a configuration known as the tetraneutron. This isn't just defying logic, it's like seeing a perfectly balanced house of cards built on a foundation of smoke. The first tantalizing hints emerged from a landmark experiment in 2002 at the Ganel Accelerator in France. Researchers weren't even hunting for this mythical particle, they were studying a different nuclear reaction. They fired a beam of helium-8, a rare and unstable isotope, into a target of carbon-12. In the resulting subatomic debris, they observed four neutrons being ejected simultaneously. The real surprise was in the energy signature of these four neutrons. Their properties suggested they weren't just four individual particles flying apart randomly, but were instead momentarily linked, forming a short-lived resonant state, a tetraneutron that existed for just a fleeting fraction of a nanosecond before disintegrating. This was like seeing the brief, perfect shape of a soap bubble the instant before it pops. The physics world was electrified but also deeply skeptical. The result was so revolutionary that many believed it had to be a misinterpretation, a statistical fluke, or an error in the complex analysis of the collision data. For over a decade, the tetraneutron remained a controversial specter. The theoretical challenge was immense. Our best models of nuclear forces, refined over decades, could not easily accommodate this four-neutron party. The strong force prefers to act between proton-neutron pairs. A system of only neutrons lacks the charge distribution that helps create a stable bond. It was like trying to build a structure with magnets that only have their north poles. They would all repel each other. theorists struggled to find a mechanism that could overcome this tremendous repulsion, even for a fleeting moment. Some proposed that the tetraneutron wasn't a true bound state but a type of exotic resonance, a temporary, meta-stable configuration that exists just at the edge of stability, held together by a delicate quantum mechanical dance. The debate was finally pushed toward a resolution by a more direct and precise experiment nearly 2 decades later. In 2016, a team in Japan used a different approach. They collided a beam of helium-4 nuclei with a target of liquid helium, creating helium-8 isotopes in the process. By meticulously measuring the energy and angles of the reaction products, they were able to provide much stronger evidence for the tetraneutron's existence, pinning down its likely energy and incredibly short lifetime. Then, in 2022, researchers at the Technical University of Darmstadt in Germany achieved what many considered the smoking gun. They succeeded in directly observing the decay of a tetraneutron after creating it in a carefully controlled reaction. This wasn't just inferring its existence from missing energy, this was watching it live and die. The data indicated this entity survived for about 1 × 10⁻⁻22 seconds, an almost incomprehensibly brief flash of existence, but long enough in the quantum world to be considered a genuine, if ephemeral, particle. So if it does exist, what holds it together? The leading theory is as beautiful as it is strange. It may involve what's called the Efimov effect, a quantum phenomenon where certain particles can form stable 3-body systems through a subtle interplay of forces, even when no 2 of them can bind together directly. Perhaps the tetraneutron is an Efimov state of 4 neutrons, a delicate structure where each neutron indirectly influences the others in a complex, coordinated way that only works as a quartet. This would be an entirely new and unexpected manifestation of the strong force, one that operates not through direct attraction, but through a kind of quantum choreography that we are only beginning to understand. The implications of this discovery ripple far beyond the lab. If neutrons can bind to each other in small clusters, even briefly, it could revolutionize our understanding of neutron stars, those incredibly dense corpses of massive stars. The core of a neutron star is an environment of almost unimaginable pressure, where the rules of nuclear physics are pushed to their absolute limit. The presence of tetraneutrons, or even larger neutron clusters, could dramatically alter our models of the matter that exists in these extreme states. It could change how we calculate the star's density, its cooling process, and even the gravitational waves it might emit in a collision. The humble, impossible tetraneutron, a particle that lives for less than a blink of an eye, might just be the key to unlocking the secrets of the most mysterious objects in the cosmos. Yet, even as we uncover exotic particles and ghostly galaxies, a more fundamental accounting error has been plaguing cosmologists for decades, one that hits closer to home than dark matter or dark energy. This isn't about the invisible 95% of the universe. This is about the 5% we thought we understood the normal matter that makes up every star, planet, and person. When scientists add up all the normal matter, or baryons, they can see in the nearby universe all the stars, gas clouds, and dust. The numbers come up shockingly short. We can only account for about half of the baryons that should be there, based on our precise measurements of the early universe from the cosmic microwave background. It's a cosmic missing matter problem, a case where half the atoms in the universe seem to have simply vanished without a trace. This discrepancy isn't a small oversight, it's a gaping hole in our inventory of reality. The CMB provides a pristine record of the universe's contents when it was only 380,000 years old, and it tells us exactly how much normal matter was present at that time. The laws of physics are very clear. Matter cannot be created or destroyed, only transformed. So all those baryons from the infant universe have to be around today somewhere. They didn't disappear, they're just hiding in plain sight, and for a long time we lacked the tools to find them. The leading suspect for this hiding place is a diffuse, incredibly hot gas that permeates the vast spaces between galaxies, known as the warm-hot intergalactic medium, or WIM. Imagine the cosmic web not as a structure of shining galaxies, but as a network of nearly invisible filaments, like the delicate veins in a leaf. These filaments are made of dark matter, but they are also traced by ordinary matter in the form of this superheated WIM. The gas in these regions is so hot, ranging from hundreds of thousands to millions of degrees Celsius, that it doesn't emit light in a way our traditional telescopes can easily detect. It's also too diffuse to block the light from objects behind it. It's the ultimate cosmic camouflage, a fog so tenuous and energetic that we simply couldn't see it, even though we knew it had to be there. Finding it required a new kind of cosmic detective work, using some of the most violent and energetic events in the universe as our flashlights. The breakthrough came from using fast radio bursts and brilliant quasars as backlights. When the light from these incredibly distant, bright sources travels across the universe to reach us, it passes through these filaments of the WIM. The hot gas in these filaments doesn't block the light entirely. Instead, it leaves a tiny, telltale fingerprint by absorbing very specific wavelengths of light. The gas is so hot that it strips electrons from atoms, creating a soup of charged particles known as a plasma. This plasma imprints extremely faint absorption lines on the light passing through it, corresponding to highly ionized oxygen and other elements. Detecting these ultra-faint lines is like trying to find the silhouette of a specific thread in a tapestry by studying the shadow it casts from a mile away. It requires incredibly sensitive spectrographs on the world's most powerful telescopes. Recent observations have finally started to succeed. By meticulously analyzing the light from hundreds of quasars, astronomers have begun to map this hidden reservoir. They look for the subtle dip in intensity at the specific wavelength that corresponds to oxygen that has had 5 of its 8 electrons stripped away. This signature, known as O6, is the gold standard tracer for the WIM. In a series of painstaking studies, these signals have been detected, confirming that a significant portion of the universe's missing baryons are indeed tied up in this vast, hot web. The filaments are there, and they are filled with the atoms we've been searching for. The story doesn't end there. Fast radio bursts have emerged as an even more powerful tool for this hunt. As we discussed earlier, the dispersion of an FRB's signal tells us the total number of electrons it encountered on its journey. Since most of these free electrons are in the diffuse gas between galaxies, each FRB provides a direct measurement of the total amount of normal matter along its specific line of sight. By collecting a large number of these measurements from bursts coming from all different directions and distances, astronomers are essentially performing a cosmic census, weighing the intergalactic medium and confirming that the numbers are finally starting to add up. The missing matter has been found. It was never missing, we just needed to learn how to see it. This discovery closes a major chapter in cosmology, affirming that the universe is not disobeying its own rules. We just had to develop the right tools to read the fine print. But if the missing baryons represent a case of cosmic matter hiding in plain sight, our next discovery presents a paradox where particles arrive from deep space that, by all rights, should have been completely lost along the way. This is the Greisen-Zatseping-Kuzmin, or GZK, paradox, and it hinges on a fundamental prediction about the journey of the most energetic particles in the universe. According to a limit established in the 1960s by those 3 physicists, there should be a hard cutoff in the energy spectrum of cosmic rays arriving at Earth. The universe itself should act as a natural shield, preventing the most powerful particles from ever completing their intergalactic voyages. Yet our detectors have recorded them anyway, leaving scientists with a stunning violation of a seemingly unbreakable cosmic speed limit. To understand this paradox, we need to follow the incredible journey of a single proton accelerated to nearly the speed of light by some cataclysmic event billions of light years away. This proton, an ultra-high-energy cosmic ray, carries as much kinetic energy as a well-thrown baseball, all compressed into a single subatomic particle. As it streaks across the universe, it isn't traveling through empty space. It's moving through a sea of radiation left over from the Big Bang, the cosmic microwave background. For this proton, these harmless microwave photons are not just a faint glow, they are a deadly obstacle course. Because the proton is moving so close to light speed, from its perspective, these low-energy CMB photons are massively blue-shifted into the range of high-energy gamma rays. When a proton with that much energy smashes into a gamma-ray photon, something very specific happens. It creates a new particle, specifically a pion. This interaction robs the proton of a significant fraction of its energy. The math is brutally clear. Any proton with an energy above about 6 times 10 to the power of 19 electron volts will interact with the CMB so frequently over a distance of 100 million light-years that it will be slowed down below this energy cutoff long before it could ever reach us from a distant galaxy. This calculated boundary is the GZK limit. It effectively creates a cosmic horizon for such particles. We should only be able to see ultra-high-energy cosmic rays that originate from within our own local galaxy cluster, where the journey is short enough to avoid too many collisions. The problem is, our local neighborhood doesn't contain any objects powerful enough to accelerate particles to these insane energies, so the detection of any cosmic ray above this limit is a major puzzle. Despite this theoretical barrier, observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah have repeatedly recorded these rule-breaking particles. They detect them not by catching the particle itself, which is often a single proton or atomic nucleus, but by observing the massive cascade of secondary particles it creates when it slams into the top of our atmosphere, a sprawling air shower that can spread over dozens of square kilometers. The energy of the primary particle is calculated from the size and development of this shower, and the results are unambiguous. These particles exist, and they are arriving from all directions with energies far exceeding the GZK limit. The shield has been breached and the paradox is very real. So how are they getting here? Scientists are exploring several compelling explanations, each more fascinating than the last. The first possibility is that our understanding of particle physics is incomplete. The proton-photon interaction that produces pions is governed by the theory of special relativity and well-tested particle physics. But at these extreme energies, could the rules be changing? Some theories, including certain versions of quantum gravity, suggest that Lorentz invariants, a cornerstone of Einstein's relativity, might break down at these scales. This could mean that the energy threshold for creating pions is subtly different, or that the interactions are less efficient, allowing the protons to travel much farther than we think without losing their energy. Finding evidence for this would be revolutionary, a glimpse of physics beyond the standard model written in the sky. The second, and perhaps more likely, explanation points to the sources themselves. Maybe these ultra-high-energy cosmic rays aren't coming from billions of light-years away after all. Perhaps they are born in nearby cosmic accelerators within the GZK horizon of 100 million light-years or so. The challenge is identifying what these accelerators could be. Active galactic nuclei, the incredibly energetic cores of galaxies powered by supermassive black holes, are prime suspects. Their massive jets could potentially funnel and accelerate particles to these tremendous energies. Other candidates include gamma-ray bursts, the most explosive event since the Big Bang, or perhaps even gigantic magnetic fields associated with galaxy clusters. The search is on to correlate the arrival directions of these particles with known celestial objects, but so far, no smoking gun has been found. The particles seem to arrive fairly uniformly from across the sky, which is strange if they are coming from a small number of nearby powerful sources. This leads to a third, more complex idea, that the particles aren't protons at all. the Pierre Auger Observatory data suggests that at the very highest energies, the cosmic rays might actually be heavier atomic nuclei like iron. This changes the GZK calculation significantly. A heavy nucleus has a much larger cross-section, meaning it's more likely to interact with SIMB photons, but the interaction is different. Instead of always losing a large fraction of its energy in one go by producing a pion, a nucleus can be gradually eroded. A CMB photon might simply knock off a neutron or a proton from the nucleus, a process called photodisintegration. This allows the remaining nucleus to retain a much larger fraction of its original energy, potentially enabling it to travel farther than a proton could. If confirmed, this would resolve the paradox by showing that the highest energy messengers are not protons breaking the limit, but sturdy nuclei running a grueling but survivable cosmic gauntlet. The GZK paradox remains a wide-open frontier in astroparticle physics. It is a beautiful example of a decades-old prediction actively shaping our search for answers, forcing us to question both the behavior of matter at its most extreme and the identity of the universe's most powerful particle accelerators. Each detection of a super GZK cosmic ray is not just a data point. It is a challenge, a piece of a cosmic puzzle that demands we either find the local engines capable of such incredible feats or boldly rewrite the laws of physics to accommodate these extraordinary travelers from the deep cosmos. After confronting the paradox of particles that arrive when they shouldn't, we now turn our gaze to a cosmic structure so geometrically perfect it seems to defy the very nature of the universe itself. In the vast, chaotic expanse of space, where most nebulae bloom in beautiful, chaotic swirls of gas and dust, there exists an object of startling precision, the Red Rectangle Nebula. Located about 2,300 light-years from Earth in the constellation Monoceros, this nebula is not a random cloud but an almost architectural marvel, a series of concentric rectangular shells glowing with a deep, ruby hue, making it look less like a celestial object and more like a carefully crafted piece of art or a supernatural portal suspended in the void. The story of its discovery is a classic tale of cosmic surprise. Initially identified during the 1970 Air Force Sky Survey, its true, bizarre nature wasn't revealed until the Hubble Space Telescope turned its powerful gaze upon it. Where ground-based telescopes had seen only a reddish, boxy shape, Hubble's sharp vision unveiled an intricate ladder-like structure, a set of perfectly aligned rungs expanding outward from a central star. The name Red Rectangle is a slight misnomer. It's not a single solid shape but a bipolar nebula viewed almost exactly edge-on from our perspective. If we could fly around and view it from the top, astronomers believe it would resemble a vast, glowing hourglass. But from our unique vantage point, we are treated to this incredible illusion of celestial geometry, a spectacle that immediately raises a fundamental question. How can something so perfectly square form in a universe dominated by spheres, spirals, and random clouds? The secret to this cosmic geometry lies at the heart of the nebula, a binary star system known as HD 44179. This is not a pair of stars orbiting at a great distance, but a close-knit duo locked in a tight 15.4-month dance. One of the stars is a post-asymptotic giant branch star, a sun-like star in its final death throes that has puffed off its outer layers. The other is a smaller white dwarf companion. It is the intricate gravitational waltz between these two stars that acts as a cosmic sculptor. As the dying star sheds its material, instead of expanding outward in a simple, spherical shell, the gravitational influence of its partner funnels this ejector into two opposing cones or jets shooting out from the poles of the system. Because we are looking directly down the barrel of one of these cones, the edges of the cone's walls appear to form the long sides of the rectangle. But this alone doesn't explain the distinct, rung-like concentrations of dust that create the ladder effect. This is where the chemistry becomes as fascinating as the physics. The profound red color, which is exceptionally rare in nebulae, comes from a specific type of organic molecule known as polycyclic aromatic hydrocarbons, or PAH. These are complex, carbon-based compounds that fluoresce with a distinctive red glow when excited by ultraviolet light from the central stars. But the true key to the rectangular structure might lie in an even more exotic form of matter, crystalline dust. Spectroscopic observations have revealed the presence of an unusual form of silicate dust in the nebula. In most of space, silicate grains are amorphous, meaning their atoms are arranged in a disordered, glass-like structure. However, in the red rectangle, the grains appear to be partially crystallized. This is a crucial distinction. Crystalline structures, by their very nature, form geometric shapes with straight edges and specific angles. It's possible that these crystalline dust grains are aligning themselves along the magnetic fields or within the shock fronts of the outflowing material, creating the sharp, concentric steps that give the nebula its iconic appearance. The nebula, then, might be a colossal experiment in crystal growth, happening on a scale light years across. The red rectangle is more than just a cosmic curiosity. It is a vital laboratory for understanding the life cycle of stars and the creation of complex organic molecules. The same pHs that paint it red are considered fundamental building blocks of life, the very precursors to the amino acids and nucleic acids that make up living organisms on Earth. This nebula is essentially a factory for these probiotic materials, churning them out and seeding the surrounding interstellar medium. Furthermore, it offers a precious glimpse into the fate of our own solar system. In about 5 billion years, our Sun will enter a similar phase of its evolution, puffing off its outer layers to form a planetary nebula. Will its demise create a beautiful, chaotic swirl, or could the gravitational influence of Jupiter, acting as a binary partner of sorts, impose some unexpected order on its final form? The red rectangle stands as a breathtaking reminder that the universe is not only a place of violent chaos, but also of unexpected order, where the precise laws of physics and chemistry can conspire to create structures of astonishing beauty and geometric perfection, challenging our expectations at every turn. But just when we think we've seen the full spectrum of cosmic geometry, from the rectangular nebula to the perfect voids, our own solar system delivers a shape so precise it seems to defy the very nature of chaotic weather. High above the cloud tops of Saturn, a persistent and breathtakingly perfect hexagon encircles the planet's north pole. This isn't a fleeting cloud formation or a trick of the light. It's a six-sided jet stream, a colossal hurricane 2 times wider than Earth that has maintained its geometric perfection for decades and possibly even centuries. The Saturn hexagon is a planetary wonder, a monumental structure etched into the atmosphere of a gas giant, and it challenges our understanding of how fluid dynamics operates on a planetary scale. The discovery of this feature is a testament to the power of robotic exploration. While hints of something strange at Saturn's pole were glimpsed by the Voyager spacecraft in the 1980s, it was the Cassini mission that revealed its full glory. As Saturn's northern hemisphere emerged from its long winter into spring, Cassini's cameras captured the hexagon in stunning detail. The images are astonishing. Each of the 6 sides is longer than the diameter of our own planet, and the structure rotates with a period of about 10 hours and 39 minutes, acting as a massive engine that drives the weather patterns within it. At its center lies a churning, hurricane-like storm, but it is the immaculate straight edges of the surrounding wall that truly captivate and confuse. How can a fluid atmosphere, a system defined by turbulence and chaos, spontaneously generate and maintain such a rigid geometric shape? The answer lies not in alien architecture, but in the elegant and often counterintuitive laws of fluid dynamics. Scientists believe the hexagon is a manifestation of a phenomenon known as a standing wave. Imagine a wave pattern that gets locked in place, fixed relative to the planet's rotation. On Earth, we see simpler examples of this, like the Von Karman vortex street, where alternating swirls form behind an obstacle in a fluid flow. But Saturn has no solid obstacle at its pole. Instead, the obstacle is likely a difference in wind speeds at various latitudes. The key is the tremendous shear between eastward and westward jet streams. As these currents rub against each other, they can generate instabilities that naturally settle into a stable, polygonal pattern. Laboratory experiments here on Earth have brilliantly recreated this effect. In a classic experiment, researchers placed a rotating cylinder of fluid representing Saturn's atmosphere on a spinning table. When the cylinder was spun at a different speed than the table, the fluid inside spontaneously organized into stable polygonal shapes, including a near-perfect hexagon. This demonstrated that under the right conditions of shear and rotation, geometry can emerge from chaos. The incredible stability of Saturn's hexagon, however, points to something even deeper. The planet itself is almost entirely a fluid body, a vast ball of hydrogen and helium with no solid surface to disrupt atmospheric patterns. This allows weather features to persist for extraordinarily long timescales. The hexagon is a planetary scale tattoo, a pattern ingrained so deeply into the atmospheric circulation that it simply endures season after season. It acts as a barrier, confining different chemical compounds and aerosols within its walls, which is why it often appears to have a different color than the surrounding atmosphere. This immense vortex is a self-reinforcing system, a stable solution to the complex equations that govern fluids on a spinning sphere. It is a natural wonder that reminds us that the same physics we study in a laboratory beaker can, when scaled up to the size of a planet, create wonders of breathtaking grandeur and precision. Yet, even as we map the missing matter of the cosmos and decode the geometric wonders of planetary weather, we are forced to confront a question that brings all of our exploration back home to our own future. The staggering scale of the universe, with its billions of galaxies and trillions of planets, presents us with the profound silence of the Fermi Paradox. If the universe is so vast and so old, why does it feel so empty? One possible resolution to this paradox is as sobering as it is compelling, a concept that forces us to consider our own place in the grand timeline of cosmic evolution. This is the Great Filter hypothesis, and it suggests that the path from non-life to a spacefaring civilization is not a wide open highway, but a treacherous gauntlet littered with obstacles so immense that almost no species ever makes it through. The idea was formally developed by economist Robin Hanson, and it frames the emergence of intelligent, observable life as a sequential process, a series of critical steps. Each step represents a profound evolutionary leap, and the hypothesis proposes that at least one of these steps must be incredibly improbable. A barrier so difficult to surmount that it acts as a filter that prevents virtually all potential life from progressing to the next stage. To understand its power, we can visualize this as a timeline stretching back over 13 billion years. The journey begins with the right star system forming with habitable planets, then moves to the assembly of the complex chemical building blocks for life. The next step is the emergence of the first self-replicating molecule, the jump from simple prokaryotic cells to complex eukaryotic cells with organelles, the development of sexual reproduction, the evolution of multicellular organisms, the rise of tools using intelligence, and finally, the technological leap to a civilization capable of interstellar communication and colonization. The Great Filter could be hiding at any one of these stages. The most hopeful scenario for humanity is that the Great Filter is behind us. This means we have already successfully passed the stage that eliminates nearly everyone else. Perhaps the transition from non-living chemistry to the first primitive life, abiogenesis, is the monumental hurdle. Despite our experiments, we still do not understand how this incredible jump from inert matter to a self-replicating system occurred. It might be a chemical fluke of such staggering improbability that it has only happened once in our entire galaxy. Another candidate is the leap to the eukaryotic cell. Simple prokaryotic life existed on Earth for over 2 billion years before two cells merged in a miraculous endosymbiotic event, creating the complex cellular machinery that made all plant and animal life possible. If that specific cooperative merger is the cosmic anomaly, then the galaxy could be filled with bacterial slime, but utterly silent of any complex, intelligent voices. In this optimistic view, we are the rare exception, the lucky ones who made it through the bottleneck. The silence of the cosmos is not ominous, it is a sign that we are alone and the stars are ours to inherit. The far more terrifying possibility is that the great filter still lies ahead of us. This is the scenario that should give every person on Earth pause. It suggests that the steps we have already taken are relatively common, and that the true galaxy-clearing obstacle is one that every advanced civilization inevitably faces: self-destruction. The development of technological intelligence might carry with it the seeds of its own annihilation. This could take many forms. Nuclear war has been the classic example since the dawn of the atomic age, a single, civilization-ending conflict that leaves a world in radioactive ruins. But other, more subtle filters have emerged: a runaway climate catastrophe, an engineered pandemic released either by accident or through malice, the unforeseen consequences of nanotechnology that transforms the entire biosphere into gray goo, or the rise of a super-intelligent artificial intelligence whose goals are misaligned with the survival of its creators. The filter may not even be a single event, but a gradual stagnation. Perhaps the allure of virtual reality and simulated worlds is so satisfying that no civilization ever bothers to reach for the stars, eventually fading away in a state of comfortable decline. If the filter is ahead of us, then every flash of a radio telescope searching for signals is not a search for friends, but a search for ghosts, a warning of what may inevitably await us all. What does this mean for humanity's prospects? The Great Filter is not a prediction of doom, but a framework for profound risk assessment. It forces us to identify which steps are truly difficult. If the filter is behind us, then our future is potentially vast and open. But if it is ahead, then our most critical mission is not to find other life, but to survive. It makes our present moment in history arguably the most important we will ever face. Navigating the next few centuries with wisdom, foresight, and a global commitment to managing existential risks becomes the single greatest project of our species. The silence from the cosmos could be the loudest warning we will ever receive, a cautionary tale written in the emptiness of space, urging us to grow up and secure our future before we become just another silent data point in the galaxy's great graveyard. But if the Great Filter asks us to confront the terrifying possibilities of our future, our next discovery pulls us into the deepest, most fundamental layer of reality to question the nature of existence itself. We've explored the vast cosmic web and the peculiar behavior of planets, but now we must grapple with a truth so strange it redefines the very concept of nothing. For centuries, we imagined the vacuum of space as a true void, an empty stage upon which the drama of the cosmos plays out. But modern physics reveals this stage is not empty at all. It is a seething, bubbling, frenetic sea of energy, alive with spontaneous activity. This is the world of quantum vacuum fluctuations, where the very idea of nothing ceases to have any meaning. This bizarre phenomenon is a direct consequence of Heisenberg's famous uncertainty principle, which states that on the tiniest scales there is a fundamental trade-off between energy and time. It is impossible to know both the exact energy of a system and the exact time at which you measure it. This isn't a limitation of our instruments, it's a built-in feature of the universe. This uncertainty allows for an incredible loophole. For fleeting moments, energy can be borrowed from nowhere as long as it is paid back almost instantaneously. This borrowed energy manifests as pairs of virtual particles, a particle and its antiparticle, that spontaneously blink into existence from the void. They exist for an unimaginably short time before they inevitably collide and annihilate each other, returning the energy to the vacuum and vanishing without a trace. This isn't a theoretical fantasy, it's happening everywhere all the time. Every single cubic centimeter of what you call empty space is a tempest of creation and destruction, with countless virtual particle pairs flashing in and out of existence billions of times every second. If this sounds like an abstract mathematical concept with no connection to our tangible world, consider two groundbreaking experiments that prove this quantum frenzy is undeniably real. The first is the Casimir effect, named after Dutch physicist Hendrik Casimir. Imagine two uncharged, perfectly smooth metal plates placed incredibly close together in a perfect vacuum, only a few nanometers apart. Classical physics would say nothing should happen between them. They are just two inert pieces of metal, but quantum mechanics tells a different story. In the empty space outside the plates, virtual particles of all wavelengths can pop into existence. However, in the narrow gap between the plates, only virtual particles with wavelengths that fit perfectly between them can form. This creates a pressure imbalance, with more virtual particles pushing on the plates from the outside than from the inside. The two plates are irresistibly drawn together. This tiny, measurable force has been repeatedly demonstrated in laboratories, providing direct physical proof that the vacuum is not passive but is teeming with this transient energy. The second crucial piece of evidence comes from a subtle shift in the light emitted by hydrogen atoms, known as the Lamb shift. According to the simplest model of quantum mechanics, two specific energy levels in the hydrogen atom should be identical. But in the 1940s, Willis Lamb and his colleague Robert Rutherford discovered a tiny but definite difference between them: the explanation. Quantum vacuum fluctuations, the constant appearance and disappearance of virtual particles around the electron in the hydrogen atom, slightly buffet it, changing its energy ever so slightly. This Lamb shift is not a minor curiosity. It is a critical correction that must be accounted for in our most precise quantum electrodynamics calculations. The GPS in your phone relies on ultra-precise atomic clocks, and their accuracy depends on calculations that include the Lamb shift, meaning this ghostly quantum activity is literally guiding you down the road. This leads us to one of the most profound and troubling implications of all this activity: the concept of vacuum energy. If empty space is constantly generating these particle pairs, then it must contain a baseline energy, a fundamental background hum to the universe. When theorists first tried to calculate the strength of this vacuum energy, the result was a number so catastrophically large it became known as the worst prediction in the history of physics. The calculated value was a staggering 120 orders of magnitude too large. If that number were correct, the inherent energy of the vacuum would have generated so much repulsive force that the universe would have torn itself apart instantly after the Big Bang. The fact that we exist at all means our calculation is desperately wrong, and that this vacuum energy must be almost but not quite zero. This is the infamous cosmological constant problem, and its resolution remains one of the greatest unsolved mysteries in theoretical physics. We see the effects of the quantum vacuum everywhere, yet we fundamentally do not understand why its energy is so faint, a whisper when our math screams. This bizarre reality completely shatters our classical notion of nothingness. True, absolute nothing, a complete and total void, does not exist in our universe. Every bit of empty space is a physical something, a dynamic medium with properties and structure. It can be polarized, it can exert forces, and it contains energy. This quantum vacuum is the fundamental substrate of everything. The particles we consider real and permanent are merely stable, long-lasting excitations of this eternal, fluctuating field. We are all, at the most fundamental level, waves on this restless quantum sea. It is the most counterintuitive discovery imaginable, revealing that the solid ground of reality is built upon a foundation of eternal, chaotic, and spontaneous creation. And now we turn from the quantum depths of reality to a mystery that has captured the public imagination for decades, a story that orbits not in the realm of theoretical physics, but in the very space above our heads. Suspended in the eternal night is a tale of an ancient watcher, a silent sentinel from another world that has been gazing down upon humanity for millennia. This is the legend of the Black Knight satellite, a story that masterfully weaves together misunderstood science, genuine space history, and our deep-seated desire to believe we are not alone. The myth, as it's often told, is compelling. It describes an alien satellite of unknown origin, incredibly ancient, that has been orbiting Earth for approximately 13,000 years. Proponents of the theory point to a series of strange events. In the 1890s, Nikola Tesla reportedly detected a strange, repeating radio signal while experimenting with his high-voltage Colorado Springs apparatus, which he believed could be an attempt at communication. Decades later, in the 1920s, amateur radio operators began reporting mysterious long-delayed echoes, where their own transmitted signals would bounce back to them seconds later, as if reflected by some unseen object. But the story truly captured global attention in 1960 when Time magazine reported that the U.S. Navy had detected a dark, unidentified object in orbit. To many, this was the final proof. The narrative was set. An extraterrestrial probe was circling our planet, and someone in authority finally knew it was there. The reality, as is often the case, is a fascinating lesson in how myths are born from the misinterpretation of real events. Let's untangle the history. The dark object reported by Time was not a mystery to the military. It was a newly discovered piece of space debris, a remnant from a secret Air Force project called Corona. It was the Discoverer program's payload shroud, a large black piece of mylar insulation that had peeled away from an early spy satellite during its launch. The Navy's tracking was part of the burgeoning effort to catalog objects in space, not an investigation into aliens. Nikola Tesla's signal was almost certainly interference from a natural astrophysical source, like the plasma interactions in Jupiter's magnetosphere, which we now know can produce powerful radio waves. And the long-delayed echoes, these are now understood to be a complex ionospheric phenomenon, where radio waves become trapped and take a longer path between layers of the Earth's upper atmosphere. So, what about the famous, ominous photographs? The most iconic image associated with the Black Knight is a dark, irregular shape against the curve of the Earth, taken during a 1998 Space Shuttle Endeavour mission. This is not a 13th millennium-old artifact. It is a very modern and very terrestrial piece of equipment. It is a thermal blanket that was lost during an EVA by astronaut Jerry Ross. The image is genuine, but its description as the Black Knight is a complete misidentification, a classic case of seeing what one wants to see in the vast and unfamiliar environment of space. Yet the persistence of the Black Knight myth is perhaps more interesting than the myth itself. It speaks to a fundamental human need. In the early days of the space race, the sky was a new frontier filled with both wonder and fear. The idea that we might not be the pioneers, that someone might have been there first, is a powerful and haunting thought. The myth provides a comforting, if eerie, answer to the Fermi Paradox. We are not alone, and the evidence is literally right above us, just out of reach. It transforms the cold, impersonal reality of orbital mechanics into a grand, cosmic narrative. Furthermore, the name Black Knight itself, likely borrowed from a British rocket program, carries connotations of a silent, armored, and mysterious watcher, perfectly fitting the archetype of an alien probe. The true story happening in orbit is no less incredible. Instead of one ancient satellite, our planet is encircled by a swirling shell of space debris, a testament to our own technological adolescence. Over 100 million pieces of human-made junk, from flecks of paint to spent rocket boosters and defunct satellites, travel at 17,500 miles per hour. This ever-growing cloud poses a genuine threat to active missions and the International Space Station. Organizations like the U.S. Space Surveillance Network constantly track over 27,000 of these objects, a real-time map of our own clutter against the blackness of space. In a way, the reality is more profound than the fiction. We haven't found an alien satellite, but we have created our own artificial ring, a permanent archaeological layer of the 20th and 21st centuries that will orbit our world long after our civilizations are gone. The Black Knight is a phantom, but the silent, ticking time bomb of space debris is a very real legacy we must now learn to manage. And so we return to that singular, electrifying moment in August 1977, a 72-second burst of radio energy that has echoed through the decades, refusing to be forgotten or fully explained. The WOW signal remains the ultimate cosmic tease, the one that got away, a perfect candidate for an extraterrestrial greeting that we have never been able to hear again. For over 40 years, it has sat perched at the pinnacle of SETI achievements, a reminder of both the promise and the profound frustration of the search. But science does not stand still, and neither has the investigation into this enduring mystery. New technologies, fresh perspectives, and even a controversial natural explanation have all been brought to bear on this decades-old enigma, yet the signal's true nature continues to defy a final verdict. The most significant attempt to solve the puzzle came in 2017, just as the signal was approaching its 40th anniversary. Astronomer Antonio Paris proposed a compelling and seemingly straightforward natural cause, a comet. His hypothesis centered on two comets named 266P/Christensen and 335P/Gibbs, which had been discovered after 1977. Crucially, their orbital paths indicated they would have been transiting through the exact patch of sky in the constellation Sagittarius from which the WOW signal originated. Comets are known to be surrounded by massive clouds of hydrogen gas, released as their icy nuclei are warmed by the sun. A large, gaseous coma expanding for millions of kilometers around a comet could, in theory, reflect or emit a powerful, narrowband radio signal at the frequency of 21 centimeters, precisely the frequency the Big Ear telescope was monitoring. It was an elegant solution, a cosmic coincidence where a perfectly timed celestial passerby could have mimicked the signature everyone was hoping for. The scientific community embraced the opportunity to test this idea. When Comet 266P/Christensen returned to the same region of space in 2017, multiple radio telescopes were trained upon it, ready to detect its hydrogen signature. The results, however, were definitive and disappointing. The radio emissions from the comet were far too weak, orders of magnitude fainter than the powerful signal recorded in 1977. Furthermore, the signal from a comet would be diffuse and spread out, not the sharp, intense spike that overwhelmed the Big Ear receiver. The comet hypothesis, while creative and scientifically valuable for prompting new observation, was effectively ruled out. The search for a simple answer had once again come up empty, forcing astronomers to confront the original mystery with renewed intensity. This failure only deepened the intrigue, cementing the WOW signal's status as an outlier. In the years since, more advanced sky surveys have provided a much clearer picture of that specific celestial neighborhood. We now know that the precise point of origin is not entirely empty. It lies in a region populated by solar-type stars, some with potential planetary systems. While there is no identified star exactly at the coordinates, the area is far from the complete void it was once thought to be, raising the possibility that a previously uncatalogued star could host a world capable of generating such a transmission. Modern signal processing techniques have also been applied to the original data. searching for any subtle patterns or modulations within that brief 72-second window that might have been missed by earlier analysis. So far, the signal remains stubbornly pure, a featureless blast of power with no discernible internal structure that could betray an intelligent source. The most profound development is not a new theory, but a new commitment to the search. The WOW signal's greatest lesson was the importance of follow-up. The original detection was a stunning piece of luck, but the inability to immediately point another telescope at that spot meant a potential opportunity was lost forever. Today, projects like the Breakthrough Listen initiative have learned from this. They utilize arrays of telescopes that can instantly cross-check a promising signal across different locations, or swiftly slew other instruments to observe the same patch of sky across multiple wavelengths. The entire methodology of SETI has evolved to eliminate the agonizing delay that turned the WOW signal into a permanent question mark. We are now listening not just for a single ping, but for a repeat transmission, a pattern, or a signal that persists long enough for us to truly study it. Ultimately, the enduring power of the WOW signal lies in its perfect ambiguity. It was too perfect to be easily dismissed as noise, yet too brief to be verified as a message. It occupies a tantalizing middle ground that fuels both scientific inquiry and the human imagination. It represents the possibility that we might have, just once, brushed fingertips with another intelligence, a civilization that chose that exact moment to shout into the dark, perhaps not even aware that someone was finally there to listen. It is astronomy's most famous ghost, a whisper that continues to challenge our assumptions and inspire us to keep listening, always wondering if the next signal will be another fleeting mystery or the one that finally answers back. Yet, even as we build this meticulous map of our cosmic neighborhood, a profound and troubling disagreement is brewing over the very scale of the map itself. This isn't a mystery about a strange object or a fleeting signal. It's a crisis of consistency, a fundamental crack in the foundation of modern cosmology known as the Hubble tension. At its heart is a single critical number, the Hubble constant, which measures the current expansion rate of the universe. For decades, pinning down this value has been a primary goal of astronomy. But we now have two golden, independent methods to measure it, and they are giving us two stubbornly different answers. This discrepancy isn't a small statistical error. It's a growing chasm that suggests our understanding of the universe's fundamental physics may be incomplete, forcing us to consider the existence of something entirely new. The first method uses the universe's baby picture, the cosmic microwave background, as captured by the Planck satellite. By taking this snapshot of the infant universe and running it forward through our incredibly precise standard model of cosmology, the lambda-cold dark matter model scientists can predict what the expansion rate should be today. This early universe measurement gives us a very precise value of approximately 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.3 million light-years, a galaxy should be moving away from us 67.4 kilometers per second faster. The second method measures the expansion directly in our local, modern universe. Astronomers use brilliant, reliable standard candles like Type Ia supernova and Cepheid variable stars to measure the distances to nearby galaxies with incredible accuracy. By comparing these precise distances to the redshifts of those galaxies, which tells us how fast they are moving away, they can calculate the Hubble constant directly. Teams using the Hubble Space Telescope have refined this late universe method to a razor's edge, and their answer is consistently and undeniably higher, around 73 kilometers per second per megaparsec. For years, the hope was that as our measurements became more precise, the error bars would shrink and these two values would converge, but the opposite has happened. The gap has persisted and even grown more significant, now standing at a confidence level of 5 sigma, meaning there's only a 1 in a million chance this is a fluke. This is where the powerful new eyes of the James Webb Space Telescope entered the scene, tasked with a critical mission to rule out any systematic errors in the local measurement. JWST infrared vision allows it to see straight through the dust that can obscure Cepheid variables, and it can resolve individual stars in distant galaxies with stunning clarity, providing the cleanest possible calibration of the cosmic distance ladder. The initial results from JWST have only confirmed the problem. Its measurements of the Hubble constant align perfectly with the Hubble Space Telescope's higher value, effectively slamming the door on the idea that observational error is to blame. The tension is real. With measurement error increasingly ruled out, cosmologists are now forced to entertain the thrilling possibility that the discrepancy is a sign of new physics. Our standard model, lambda CDM, might be missing an ingredient. One compelling idea is early dark energy. This theory proposes that a new, additional form of dark energy existed in the universe's first few 100,000 years. This extra repulsive force would have subtly changed how the primordial plasma oscillated, which would slightly alter the patterns we see in the cosmic microwave background. If those patterns are interpreted with the standard model, they give us one expansion rate. But if this early dark energy was present and then faded away, it would mean our prediction from the CMB is slightly off, potentially bringing it into line with the higher local measurement. It's as if a temporary booster rocket was attached to the infant universe, giving expansion an extra, forgotten kick. Another radical solution involves modifying our theory of gravity itself. Theories like modified Newtonian dynamics, or MUND, propose that gravity behaves differently on the colossal scales of galaxies and clusters than it does in our solar system. While MUND has had mixed success, the Hubble tension has inspired a new look at whether Einstein's theory of general relativity might need a tweak on the largest cosmic scales. Perhaps gravity weakens differently over time or distance than we thought, which would affect how we interpret both the early universe's evolution and the modern expansion rate. Other proposals are even more exotic, suggesting the existence of new types of relativistic particles from the early universe or that dark matter might have unusual interactive properties. The implications of resolving this tension are monumental. It's not just about getting the right number for a textbook, it's about rewriting the textbook entirely. Confirming that the Hubble tension requires new physics would be the most significant shift in cosmology since the discovery of dark energy itself. It would open a direct window into the universe's first moments and the fundamental forces that have shaped its entire history. This isn't a problem to be solved so much as a clue, a cosmic puzzle left for us by the universe, hinting that our current understanding, as successful as it has been, is merely a stepping stone to a deeper, more complex and far more fascinating reality. But what if we've been thinking about this puzzle all wrong? For decades, the dominant solution has been to invent a new, invisible substance, dark matter, to provide the missing gravity. Yet a small but persistent group of physicists has been championing a radically different approach. Instead of adding something to the universe, what if we're simply misunderstanding the laws of physics themselves? This is the core of an alternative path, a proposal that the force we call gravity doesn't operate in the vast emptiness of interstellar space in the same way it does here in our own solar system. The most developed of these ideas is known as modified Newtonian dynamics, or MUND. Conceived by physicist Mordechai Milgrom in the early 1980s, MUND starts with a beautifully simple premise. It suggests that Newton's law of gravity, which works perfectly for predicting the orbits of planets and the path of spacecraft, begins to break down in environments where gravity is incredibly weak, precisely the conditions found in the outer reaches of galaxies. In these regions, the acceleration due to gravity is so faint it falls below a critical threshold. Milgrom proposed that below this threshold, gravity switches from its familiar inverse square law to a new behavior, becoming stronger than Newton or Einstein would predict. This tiny tweak, this gentle nudge to the equations in the realm of the extremely faint, is all man needs to explain why stars on the outskirts of galaxies orbit so quickly. There's no need for halos of invisible matter. The gravity from the stars we can see is simply stronger in those distant, sparse regions than our standard textbooks would lead us to believe. And for a surprisingly long list of galaxies, MUND works astoundingly well. It doesn't just roughly fit the data, it often predicts the precise shape of a galaxy's rotation curve, the graph of orbital speed versus distance from the center, using only the visible distribution of stars and gas. For many spiral galaxies, the agreement between MUND prediction and the observed rotation is remarkably clean, a success that has kept the theory alive and fiercely debated for over 40 years. Its proponents argue that this elegance is a point in its favor. It solves the mystery with a minor modification to known physics rather than invoking a vast, undiscovered universe of particles that have eluded every attempt at direct detection. However, the universe is a demanding laboratory, and a theory must explain more than just one type of experiment to be considered complete. This is where MUND, in its original form, begins to encounter serious problems. Its most significant failure lies in the realm of galaxy clusters. When astronomers observe huge clusters of galaxies, they see two independent lines of evidence for missing mass. The first is the motion of the galaxies themselves, which are moving too fast to be held by the cluster's visible matter. The second, and more damning for MUND, is the observation of incredibly hot, X-ray emitting gas that fills the space between the galaxies. This gas is so hot that it should have evaporated and blown away long ago unless it is held in by a deep gravitational well, a well far deeper than the visible mass or even MUND-enhanced gravity can provide. To account for this, even MUND requires some form of additional, unseen matter in clusters, though far less than the standard model. The knockout blow for a pure MUND theory, however, came from a cosmic collision, the bullet cluster. This system is actually two clusters that have smashed right through each other. During such a collision, the clouds of hot gas, which make up most of the normal matter, slam into each other and slow down like two clouds of smoke merging. But the thing providing most of the gravity, as mapped by the effect of gravitational lensing, did not slow down. It sailed right through the collision, completely separate from the gas. This is a direct observational proof that the majority of the mass in these clusters is not only invisible, but also doesn't interact with normal matter or itself, exactly as dark matter is supposed to behave. It is incredibly difficult for any modification of gravity to explain why the gravitational field would become divorced from the visible mass during a collision, and yet perfectly align with it in isolated galaxies. This evidence strongly suggests that the missing mass is indeed a physical substance that can be physically separated. In response to these challenges, some theorists have developed more sophisticated successors to MUND. One of the most prominent is emergent gravity, proposed by physicist Eric Verland. This theory is far more radical, suggesting that gravity is not a fundamental force at all. Instead, Verland proposes that gravity emerges from the interactions of fundamental information bits, or entropic forces, within the fabric of spacetime. In this view, the enhanced gravity we attribute to dark matter is a side effect of the way dark energy, the energy of empty space, interacts with normal matter on large scales. It's a profound and mind-bending concept that frames gravity as a cosmic illusion, a consequence of deeper quantum processes. While mathematically elegant, emergent gravity is still in its infancy, and it struggles with the same devastating evidence from galaxy cluster collisions that plagued its predecessor. The bullet cluster remains a formidable obstacle for any theory that attempts to explain away dark matter as a misunderstanding of gravity. The debate between these paradigms is far from settled. Proponents of modified gravity point to its stunning successes in predicting galactic rotations and its elegant avoidance of inventing new particles. Advocates for dark matter highlight its breathtaking explanatory power across the entire cosmos, from the formation of the first galaxies to the precise patterns in the cosmic microwave background, and of course, the direct visual evidence from collisions. What makes this scientific tension so valuable is that it pushes both sides to refine their ideas and seek new, decisive tests. Perhaps the ultimate resolution won't be a victory for one side or the other, but a synthesis, a recognition that our current theory of gravity might need refinement and that the universe is filled with a mysterious, non-luminous substance. This ongoing struggle to explain the motion of the stars is a powerful engine of discovery, forcing us to question our most basic assumptions about the fundamental laws that govern the cosmos. Now, after mapping the cosmos from its largest structures to its smallest particles, we arrive at our final discovery, one that pulls the rug out from under everything we think we know about reality itself. It's a concept that shifts the conversation from astrophysics to philosophy, and it asks perhaps the most profound question of all: what if none of this is real? I'm not talking about a dream or an illusion, but something far more structured. What if our universe, with all its galaxies, black holes, and the very laws of physics, is nothing more than an impossibly sophisticated simulation, a cosmic video game running on a computer of godlike power in some other base reality? This is the simulation hypothesis, and while it sounds like the plot of a science fiction movie, a growing number of philosophers, technologists, and even physicists are beginning to argue that we can not only take it seriously, but that we might even find a way to test it. The core idea is ancient, echoing Plato's allegory of the cave and Descartes' evil demon, but its modern formulation is often credited to philosopher Nick Bostrom. His logical trilemma is startlingly simple. He reasons that one of three propositions must be true. First, almost every civilization at our level of technological development goes extinct before achieving the capability to create realistic simulations. Second, even if they survive, advanced civilizations almost universally lose interest in creating such simulations. Or third, we are almost certainly living in a computer simulation right now. His argument is that if even a tiny fraction of advanced civilizations avoids extinction and chooses to run vast numbers of ancestor simulations, high-fidelity recreations of their own history, then the number of simulated minds would quickly and vastly exceed the number of biological original minds. Statistically speaking, if there are billions of simulated beings for every one real being, the odds that you and I are among the real ones are astronomically small. We'd be surrounded by NPCs and not even know it, living out our lives on someone else's hard drive. But this isn't just a philosophical parlor trick. The hypothesis gains traction because it offers potential explanations for some of the deepest weirdness in quantum mechanics. Think about the strange, probabilistic nature of particles which only settle into a definite state when they are observed. In a simulation, this makes perfect sense. It's a resource-saving technique called procedural generation, the same trick used in video games to render a vast, open world without overloading the graphics card. The universe doesn't bother calculating the precise position of every electron in a rock until a conscious observer, the player character, turns to look at it. The infamous double-slit experiment, where a single particle seems to pass through two slits at once and interfere with itself, could be explained as the simulation cutting corners, only calculating the probabilistic wave function until a measurement forces it to pick a definite outcome. Quantum entanglement, that spooky action at a distance, could simply be two data points that are linked in the code, instantly updating each other regardless of their apparent separation in the rendered world. From this perspective, the bizarre rules of the quantum world aren't fundamental laws of nature. They are the glitches and optimizations of the source code, the telltale signs of a system operating with finite processing power. This leads us to the most tantalizing possibility. If we are in a simulation, could we find evidence of it? some scientists propose looking for what you might call cosmic resolution limits or rounding errors in the laws of physics. Just as a digital image breaks down into pixels when you zoom in too far, perhaps space-time itself has a fundamental graininess, a smallest possible unit of distance known as the Planck length. If we could detect evidence that the universe is not perfectly smooth but is instead pixelated at this ultra-tiny scale, it could be a sign of the underlying computational grid. Another approach is to search for anomalies in the constants of nature. The universe seems fine-tuned for life. Change the strength of gravity or the nuclear force by just a few %, and stars and planets could never form. In a natural universe, this is a profound mystery. In a simulated one, it could be evidence of deliberate tuning by the programmers. Perhaps we could even one day perform a kind of cosmic stress test, designing an experiment so computationally intensive that it would overwhelm the simulation's resources, causing a detectable glitch in the matrix, a momentary stutter in reality itself. Of course, the hypothesis is fraught with dizzying paradoxes. If our reality is a simulation, what about the reality of the beings who created it? Could they themselves be simulations within simulations, a near-infinite regress of nested realities like a set of Russian dolls? And what is the ultimate goal? Are we merely entertainment for hyper-advanced beings, a historical reenactment, or a scientific experiment to test cosmological theories? The simulation hypothesis doesn't answer the question of why there is something rather than nothing. It just kicks it up one level, leaving us to wonder about the nature and motives of our potential creators. It transforms cosmology from a search for our origins into a search for our source code, a quest to debug the universe and perhaps one day peek behind the curtain at the hardware that makes it all possible. Whether you find it terrifying or exhilarating, it forces a radical humility, suggesting that the ultimate cosmic discovery might not be a new particle or a new force, but the realization that we are living inside the greatest masterpiece of information technology ever conceived. From the ghostly tug of the Great Attractor to the quantum whispers of virtual particles, these 30 discoveries paint a portrait of a cosmos that is fundamentally, gloriously, and bafflingly weird. Each one, in its own way, serves as a stark reminder that the universe operates on a logic far grander and more complex than our own. They challenge the very foundations of what we think we know, pushing the boundaries of physics, philosophy, and our own perception of reality. It's as if every time we believe we're finally closing in on a complete theory of everything, the cosmos throws another curveball, revealing a deeper layer of mystery hidden just beneath the surface. This isn't a sign of failure, it's the very engine of scientific revolution. The greatest breakthroughs in human history have always been born from these moments of profound confusion, when the old models shatter and we are forced to see the world with new eyes. What ties these discoveries together is a humbling through line, a consistent theme of our own cosmic insignificance and our astonishing potential. We are inconsequential specks on a tiny rock orbiting an average star, yet we have managed to decode the afterglow of creation, map the invisible scaffolding of the universe, and capture particles blinking in and out of existence. We are simultaneously humbled by the vast forces we cannot control and empowered by the knowledge we have gained. This beautiful contradiction is at the heart of exploration. It tells us that the universe is not here to make sense to us, but that we are here to make sense of it, piece by perplexing piece. The journey is far from over. In fact, with every mystery we solve, two more seem to emerge, ensuring that the sense of wonder that comes from looking up at the night sky will never, ever fade. Now, we want to hear from you. After this journey through the impossible, which of these 30 discoveries most defies your own personal logic? Was it the haunting silence of the Fermi Paradox that left you wondering, or the architectural perfection of the Red Rectangle Nebula? Did the statistical nightmare of the Hubble tension break your brain, Or did the philosophical vertigo of the simulation hypothesis make you question everything? Let us know in the comments below. We read every single one and love seeing these discussions take on a life of their own. If this exploration of cosmic mysteries left you hungry for more, you're in luck. We're already working on deep dives into the strangest planets discovered beyond our solar system, the terrifying science behind false vacuum decay, and the cutting-edge hunt for quantum gravity. Make sure to subscribe and hit the bell so you don't miss what's coming next. The universe is the greatest story ever told, and we're just beginning to learn how to read it. Thank you for joining us on this voyage to the edge of understanding. Keep looking up and never stop